Hello there, and welcome to Science for Sleep, where curiosity unfolds slowly and the cosmos takes the scenic route to your dreams. Tonight, we're going to explore a place that is both fascinating and deeply unsettling, a place where the rules of reality begin to bend, twist, and shimmer in ways that seem almost impossible. We will gently step toward a black hole, not in any rush, and consider what might really happen if you were to drift closer, inch by inch, toward one of these cosmic enigmas. Before we dive into the depths, I wonder where you are right now and what the night looks like from your little corner of the universe. Perhaps the stars are peeking through clouds, or maybe you're listening in the quiet glow of a lamp, your day gently unwinding. It's remarkable, isn't it, how each of us finds ourselves here at this very moment, all of us scattered across space and time, preparing to travel together into the shadows of the universe. If you find this journey soothing or simply a comforting pause at the end of your day, I'd be very grateful if you liked the video, maybe subscribed, and shared this quiet corner of exploration with someone else who might enjoy a gentle voyage through the stars. But there's no hurry, no deadline, no need to rush your mind along. Let's allow ourselves to drift slowly, to let the imagination stretch out comfortably, even as we approach something so immense and unknowable. Black holes are often described in dramatic terms, with fire and destruction and endless swallowing of light. But tonight, we will consider them more like a slow river pulling everything toward its centre. You may have heard them called monsters, devourers, or cosmic vacuums. Yet in reality, they are neither cruel nor capricious. They simply are. A natural consequence of gravity compressed to its extreme, a place where space itself curves inward, and time begins to behave differently than we have ever known. As you imagine approaching one, think of gravity not as a violent tug, but as a gentle, persistent pull, stretching everything, from the smallest particle to the largest star, toward a singular point of unimaginable density. From afar, a black hole appears as a dark circle set against the sparkling backdrop of galaxies and nebulae, its presence betrayed only by the way it bends light and tugs on the stars near it. You might wonder what it would feel like to fall toward that darkness, to cross that invisible threshold called the event horizon, where escape becomes impossible, and yet, from a distance, nothing seems particularly alarming. The truth is, the journey toward a black hole is both subtle and dramatic, a slow unfolding of forces and experiences that challenge every intuition you've ever had about space, time, and your own body. Imagine floating in the vacuum of space, weightless, serene, and then noticing that the stars ahead of you are distorting slightly, twisting around a center that seems to hold everything in a delicate, impossible balance. Light itself bends toward that point, and your sense of distance begins to stretch and compress, as if the universe has started playing with its own geometry. In that moment, the familiar rules of motion feel like gentle suggestions rather than strict laws. Every instinct you have about falling, moving, or even looking around becomes something to reconsider, and yet, if you allow yourself to breathe and observe, the experience is more contemplative than terrifying. There is a quiet majesty in the way gravity behaves at these extremes, a reminder that the universe is far stranger and more intricate than any clock, any calendar, or any human schedule could ever capture. While we prepare to explore these concepts, let's pause for a moment to reflect. Have you ever imagined being in a place where your sense of time itself begins to bend, where seconds might stretch endlessly or collapse into one another? Have you considered the possibility that the very passage of life could alter as you approach something so dense that even light cannot escape its pull? These questions are not just for scientists or mathematicians. They touch something deeply human, the curiosity that drives us to look up at the night sky, the wonder that makes us imagine what lies beyond what we can see, and the quiet thrill of thinking about extremes that will never touch our daily lives. And yet it is exactly this paradoxical mixture of closeness and distance, understanding and mystery, that makes black holes such perfect companions for an evening of gentle exploration. You're not falling yourself, at least not in this room, but your mind is free to drift, to trace the paths of objects spiraling inward, to feel the pull of gravity in a way that is safe, contemplative, and strangely comforting. There is an intimacy to imagining yourself in this scenario, as if for a moment you are part of the universe's grand rhythm, a tiny observer tracing the silent patterns of space, noticing the subtle twists of time, and marvelling at the astonishing coherence of natural law under the most extreme conditions. In the distance, stars continue their slow, patient rotations, nebulae pulse in soft colours, and black holes, unseen yet undeniable, anchor the motions of everything around them. They are reminders of forces so immense that our everyday experiences scarcely prepare us for them, yet they invite reflection rather than fear. Gravity, mass, light and time all meet here, and we in our quiet way are invited to witness the choreography of the cosmos. So, as we let our minds drift gently toward the event horizon, as we imagine the stretching and curving of space-time, consider the question: what would it really feel like to fall into something that challenges the very definitions of direction, duration, and distance? It's not just a story about destruction or disappearance, but about perspective, about the fragile and fascinating ways our human intuition meets the extremes of the universe. And it is this intersection, this softly bending boundary between what we know and what we can only imagine, that will guide our journey tonight. Let's begin slowly, noticing the subtle forces, the gentle distortions, and the way that gravity communicates without words, without rush, only through its quiet, inescapable influence. Step by step, second by second, we approach the edge, ready to explore the astonishing truths of black holes, allowing curiosity to move freely, letting questions unfold naturally, and permitting the mind to wander in the serene rhythm of the cosmos. Let's consider the nature of black holes, these invisible monsters of the cosmos. The term monster might sound frightening, and perhaps it is, but it's more an acknowledgement of scale, a recognition of forces that dwarf anything in our everyday lives. Black holes are not monsters in the sense of malice or intent. They do not chase or devour out of curiosity or hunger, but they are extremes, points in the universe where matter is compressed so tightly, so completely, that the rules we take for granted begin to bend and twist. From a distance, black holes are deceptively simple. They appear as a dark circle, a shadow against the backdrop of twinkling stars, galaxies stretching out across the universe like scattered jewels. You might imagine them as holes in the sky, empty spaces where nothing exists, but that is not quite true. A black hole is defined by gravity, the invisible, persistent pull that accumulates from mass concentrated into a single point. Gravity in this sense is not violent. It is an organizing principle, an invisible sculptor of space, patiently drawing everything inward, folding light and matter alike into the dense core. The center, the singularity, is where density becomes extreme, and our conventional understanding of physics begins to fail. Here, the equations that govern motion, energy, and even time no longer behave in the ways we expect. The singularity is not a place you can see or touch. It is a mathematical point where all known quantities, mass, density, curvature of space-time, are infinite, yet it exists in a framework we can only describe, never fully imagine. Surrounding this core is the event horizon, the boundary at which escape becomes impossible. Cross it, and even light, the fastest thing in the universe, cannot find a way out. To an outside observer, objects approaching this threshold appear to slow, to freeze, as if time itself hesitates at the edge. Despite the dramatic labels, black holes come in different sizes and types. There are stellar black holes, born from the collapse of massive stars after they exhaust their nuclear fuel. A star much larger than our Sun can, under the weight of its own gravity, implode into a point smaller than a city yet containing many times the Sun's mass. Then there are supermassive black holes, those behemoths lurking at the centres of galaxies, including our own Milky Way. These giants contain millions, even billions of times the mass of our Sun, and their presence organises entire galaxies, guiding stars along invisible highways, orchestrating the dance of cosmic structures. There is even a category of intermediate black holes, a size range still mysterious to astronomers, hinting at processes we are only beginning to understand. What is truly remarkable is that black holes are defined more by what they prevent than what they create. They do not radiate light in the traditional sense. They are invisible except through their influence. They are detected by the way they bend the space around them, tugging on nearby stars or pulling in gas that heats up and glows brightly before crossing the event horizon. Astronomers measure these effects, tracing the invisible shape of a black hole by watching how light, matter, and energy respond to its presence. Even when we cannot see a black hole directly, we can witness the ballet of the cosmos choreographed around it, the graceful arcs of orbiting stars, the spiral of gas caught in a silent, relentless dance. Imagine, if you will, floating in a spacecraft nearby, the stars spinning slowly in your field of vision, and a black hole at a distance bending the paths of light. You might notice the familiar constellations appearing slightly distorted, stretched into arcs and curves. The night sky would shimmer strangely, as if seen through a subtle lens crafted by gravity itself. This is gravitational lensing, one of the most elegant and quiet manifestations of a black hole's power. Light from distant galaxies and stars curves around the mass, creating arcs, duplicates, and even rings of light that trace the invisible shape of the central mass. The effect is mesmerizing and, in a way, comforting, because it is predictable. Even at the edge of what seems unknowable, the universe behaves with quiet consistency. Black holes are also surprisingly slow in their influence when considered on human timescales. Stellar matter may orbit them for millions of years before being drawn inward, while light from nearby stars may shimmer and bend over centuries. And yet, the gravitational pull at the event horizon is so immense that once crossed, escape becomes impossible. It's a gentle reminder that extremes do not announce themselves with drama. They are quiet, patient, and absolute, waiting for the universe to respond on its own rhythm. The formation of black holes is equally serene and violent, a paradox that seems uniquely suited to the cosmos. Consider a massive star at the end of its life. Nuclear fusion in its core slows and eventually ceases, and without the outward pressure from fusion to balance gravity, the star collapses inward. This collapse may trigger a supernova, an explosion that briefly outshines an entire galaxy, scattering material outward to seed future stars, planets, and perhaps life itself. At the centre of this explosion, if the remaining mass is sufficient, a black hole emerges, compact, invisible, but fundamentally reshaping its cosmic neighbourhood. We also observe that black holes can grow quietly, slowly, over billions of years. Matter falling in adds mass, bending space-time more and more tightly, while energy released in the process can trigger jets and radiation detectable across vast distances. Despite their reputation as destructive monsters, black holes are as much creators as they are consumers, shaping the distribution of stars and galaxies, influencing the paths of cosmic evolution. In a very real sense, they are architects of structure in the universe, invisible yet commanding, patient yet transformative. From a physics perspective, the study of black holes challenges everything we understand about space, time, and matter. The combination of immense mass, extreme gravity, and the event horizon creates an environment where general relativity predicts behavior that seems almost alien. Time dilates, light bends, and even causality, the order of cause and effect, begins to blur in thought experiments. The singularity represents a point where current physics breaks down entirely, inviting questions that reach into the deepest mysteries of quantum mechanics, gravity, and the nature of reality itself. But black holes are not just theoretical curiosities. They are tangible objects, detectable through gravitational waves when they merge, through the swirling light of accretion disks, and now even through direct imaging, like the famous photograph of the supermassive black hole at the centre of M87. These observations confirm what was once speculation, transforming invisible monsters into measurable, comprehensible phenomena. And yet, despite this growing understanding, black holes remain enigmatic, inviting reflection, curiosity, and a sense of quiet awe. Consider the psychological effect of thinking about a black hole. Even without leaving your chair, your mind begins to stretch, imagining forces that dwarf everything familiar. You may feel a subtle vertigo at the thought of falling toward an event horizon, a sense of dislocation as time and space begin to behave differently. These feelings are natural. They are echoes of the same awe that inspired early astronomers to look up at the night sky and wonder about the vastness beyond their own village, the uncharted depths of night, and the slow, patient passage of celestial bodies. And so the invisible monsters we call black holes are not merely destructive. They are mirrors, reflecting the limits of our perception, our understanding, and our imagination. They reveal that the universe is far more intricate than the simple motions of planets and stars we observe daily. They remind us that there are scales, forces, and truths so extreme that the mind can only grasp them indirectly through mathematics, observation, and careful reasoning. And in this recognition, there is comfort. We see order emerging from extremes, predictability within the seemingly chaotic, and a rhythm, however alien, that binds even the most extreme phenomena into the coherent universe we inhabit. As we let this understanding settle, we notice that approaching a black hole is not simply falling into darkness. It is entering a space where light, time, and matter behave differently, where observation, perspective, and reality begin to intertwine in ways both strange and fascinating. It is a reminder that the universe is not merely a stage upon which events unfold, but a vast dynamic system of relationships, connections, and interactions, where even invisible monsters serve a purpose, shaping the cosmos in ways that are subtle, profound, and endlessly intriguing. And so, as we prepare to move closer, to consider what it might actually feel like to approach and eventually cross the event horizon, we carry with us an awareness of the black hole's nature. It is invisible, yes, but it is also deeply present. It is extreme, yet patient. It is unknowable in detail, yet understandable through patterns, effects, and careful observation. Let's take a moment to consider the subtle and pervasive presence of gravity, the force that shapes every corner of the universe, yet often goes unnoticed in our daily lives. Gravity is not only a pull toward the centre of planets, nor merely a force keeping our feet planted on Earth. It is the invisible hand that bends space and time, weaving the very fabric of reality into patterns both gentle and profound. Imagine, if you will, a soft, elastic blanket stretched across a frame. Place a heavy ball in the centre, and notice how the fabric curves, dipping under the weight, creating a subtle well that affects everything around it. This is, in essence, what gravity does on a cosmic scale. The stars, planets, and even light itself follow the contours of this stretched fabric, tracing the paths dictated by curvature, bending and moving along invisible grooves shaped by mass. As we approach a black hole, the blanket stretches more dramatically, not abruptly but with increasing intensity. Gravity does not announce itself with forceful shouts. Instead, it gently, relentlessly tugs at everything in its vicinity. A spaceship drifting near a black hole would feel this pull as a slight, constant nudge at first, so subtle that it might almost be imperceptible, like the faint tug of a spring under tension. Yet as one nears the event horizon, The effect grows, a quiet crescendo in the cosmic symphony, drawing you forward with inexorable inevitability. The curvature of space and the slowing of time occur not in violent explosions, but as a graceful stretching of reality itself, a patient unfolding of physics that is both beautiful and disquieting. Consider how we understand this from a human perspective. On Earth, gravity is familiar, mundane even, a constant we rarely notice beyond a trip or a stumble. We are accustomed to the gentle downward pull that keeps our bodies moving predictably, the rhythm that allows us to walk, jump and run. Yet near a black hole, gravity behaves according to Einstein's general relativity, which describes it not as a simple force, but as the bending of spacetime itself. Mass tells spacetime how to curve, and spacetime tells matter how to move. This relationship transforms gravity into a silent dynamic architecture, a set of invisible pathways that guide the motions of stars, light, and even our hypothetical spacecraft as it drifts closer. Imagine floating just above the event horizon, the outer edge of a black hole where escape becomes impossible. Here, the fabric of space is stretched, the blanket bent so sharply that distances along different directions are no longer equal. The top of a spacecraft might be centimetres farther from the singularity than the bottom, yet the difference feels infinitely more profound. This stretching, this gentle yet inexorable pull, is known as a tidal force, and it is one of the most defining features of approaching a black hole. Tidal forces do not strike with heat or sound. They manifest as the elongation of objects, the slow, almost imperceptible stretching along the direction of gravity. Bodies approaching this threshold may eventually be drawn into what scientists poetically call spaghettification, a process where matter stretches into long, thin forms under the influence of these extreme gradients in gravity. And yet the experience is different depending on the size of the black hole. For a stellar mass black hole, tidal forces become extreme well before reaching the event horizon. The difference in gravitational pull between the head and feet of an astronaut would stretch the body dramatically, perhaps beyond recognition. For a supermassive black hole, however, the event horizon is so vast that tidal forces near it might initially feel gentle, almost imperceptible, giving the illusion of safe passage for anyone crossing the boundary. The difference in scale, the silent variation in forces, highlights the universe's capacity for extremes, the way cosmic phenomena can be simultaneously terrifying and subtle, destructive and delicate. Gravity also warps time, an effect that becomes increasingly pronounced as one nears a black hole. Time, which feels constant in our everyday lives, slows in regions of intense gravity, an observation that can be measured and predicted with astonishing precision. To an outside observer, someone approaching the event horizon appears to slow down, almost frozen in motion. Seconds for the distant viewer stretch into minutes, hours, and even years in extreme cases, while the person falling experiences the journey at a seemingly normal pace. This phenomenon, called gravitational time dilation, is not a trick of perception. It is a real effect of the curvature of space-time, an elegant consequence of Einstein's theory, reminding us that time and space are deeply intertwined, woven into the same cosmic fabric as gravity itself. As we drift inward, imagining the subtle pull and the stretching of both space and time, the universe appears less like a rigid framework and more like a living, responsive medium. Light bends, paths curve, and even the perception of simultaneity, the sense that two events happen at once, becomes relative. Near the black hole, what one observer considers a single moment might appear stretched or compressed to another. The gentle blanket of space-time is not uniform. It responds to mass, warps under pressure, and communicates its influence to everything that enters its domain. Observing this indirectly, we begin to appreciate the quiet intelligence of the universe, how order emerges naturally from the interplay of forces, and how extremes like black holes illustrate the principles of general relativity in ways both subtle and profound. Even before crossing the threshold of the event horizon, we can consider the effect on light. Photons, the smallest packets of light, follow the curves dictated by the black hole's gravity, creating arcs, distortions, and multiple images of the surrounding universe. This phenomenon, gravitational lensing, transforms the familiar star field into a kaleidoscope of twisted light, highlighting the curvature of space in a way that is both scientifically measurable and visually striking. The universe, in this sense, becomes a living map of gravitational influence, a record of how mass bends both space and time, tracing the invisible structures that organize everything from tiny particles to entire galaxies. Gravity also affects energy in subtle ways. As matter spirals inward, drawn closer to the event horizon, it accelerates, heats up, and emits radiation. The accretion disk, formed by matter orbiting just outside the event horizon, can shine more brightly than an entire galaxy, converting gravitational energy into light and heat. Even in this extreme scenario, the process is governed by the same laws that guide a falling apple on Earth, only amplified to unimaginable degrees. The quiet elegance of these interactions underscores the continuity between the familiar and the extreme, reminding us that physics operates with remarkable consistency, whether in a kitchen or in the vicinity of a black hole. As we imagine the pull, the stretch, and the warping of space-time, it is helpful to return to the metaphor of the cosmic blanket. Place a heavy object in the center and notice the gentle curvature of the fabric. Place a second object nearby and observe how it follows the curves, orbiting, drawn by the invisible architecture. This is how gravity shapes the motions of stars, planets, and light near a black hole. The blanket is elastic, responsive, and unyielding, bending under mass, guiding paths, and enforcing rules that are invisible yet inescapable. Crossing the event horizon is like passing the edge of this well, beyond which escape is impossible, yet the stretching and curvature leading up to it are gradual, predictable, and comprehensible. Even more intriguing is the way gravitational pull communicates across vast distances. Black holes do not act in isolation. Their influence can shape galaxies, dictate the rotation of stars, and even trigger waves in the fabric of space-time, known as gravitational waves. These ripples travel across the universe at the speed of light, carrying information about the movement and collisions of massive objects. In this way, black holes are not only zones of intense gravity, but also storytellers, sending subtle signals across the cosmos, revealing the dance of matter and energy in ways that are measurable and profound. Approaching a black hole also alters perception, not in the literal sense of vision, but in how one understands space and time. Distances appear skewed, the passage of time slows, and events unfold with a new logic dictated by the curvature of space-time. These changes are not instantaneous. They emerge gradually, allowing a careful observer to notice the subtleties of the shift, the stretching of space, and the pull of gravity without the need for drama or alarm. It is this patient unfolding, the gentle yet absolute influence of gravity, that defines the experience near a black hole and illustrates the extraordinary interplay between mass, space, and time. It becomes clear that the universe is not merely a backdrop for our lives, but an active, dynamic medium. Gravity shapes everything, from the motion of planets to the twisting of light, from the acceleration of matter to the very flow of time itself. A black hole is an extreme expression of this principle, a region where the blanket of space-time is stretched to its limits, pulling everything inward, bending reality, and demonstrating the subtle power of mass and curvature. The experience of approaching this region is not a sudden confrontation with chaos, but a gradual contemplative immersion into a realm where the ordinary rules bend, the familiar becomes strange, and the invisible architecture of the cosmos becomes evident in the most profound and gentle ways. Gravity, extreme though it may be near a black hole, is not an enemy. It is a sculptor, a guide, and a constant presence, teaching us about scale, about time, about the interplay between mass and motion. There is a moment, if we imagine it carefully, when distance begins to lose its familiar meaning. You're no longer simply far away from something in the ordinary sense, like standing across a room or even orbiting a distant planet. Instead, the space ahead of you starts to behave differently, subtly at first, almost politely, as though the universe is adjusting the rules without announcing the change. The black hole, which once appeared as a distant distortion in the starfield, now feels present in a way that is difficult to describe, not because it grows larger in a dramatic sense, but because everything around it begins to respond more noticeably to its influence. Picture yourself drifting steadily closer, not accelerating wildly, not tumbling out of control but moving in a calm, continuous glide. The stars behind you remain sharp, but those ahead begin to curve slightly, their positions bending around the darkness. It is not chaotic. In fact, it is strangely orderly, as if the universe is following a set of instructions so precise that even the distortion feels smooth and deliberate. Light itself is no longer travelling in straight lines. Instead, it traces arcs through space, wrapping around the black hole, creating a halo-like effect known as the photon sphere, where light can orbit temporarily before escaping or falling inward. At this stage, nothing physically dramatic has happened to you yet. Your body feels normal. Your breathing, your thoughts, even your sense of balance remain unchanged. And this is one of the most surprising aspects of approaching a black hole. There is no sudden wall, no glowing barrier, no cosmic alarm signalling that you are nearing a point of no return. The event horizon does not look like a surface. It does not shimmer or flicker. It is not a line drawn in space that you can point to and say, there it is. Instead, it is a boundary defined by possibility, by what can and cannot happen. The event horizon marks the distance from the centre of the black hole at which the escape velocity equals the speed of light. In simpler terms, it is the point beyond which nothing, not even light, can travel fast enough to move away. But this description, while accurate, doesn't quite capture what it feels like to approach it. Because from your perspective, there is no sudden shift. You're not abruptly stopped or pushed back. You simply continue forward, carried along by the curvature of space-time itself. Now, something subtle begins to happen with time. Not your personal sense of time, not the ticking of your own thoughts, but the way time behaves relative to everything else. To a distant observer, someone watching you from far away, your movement appears to slow down. Not gradually in the way we're used to, like a car easing to a stop, but increasingly, dramatically, as though each second of your motion is being stretched longer and longer. You seem to linger, suspended near the edge, your image dimming and reddening as the light you emit loses energy climbing out of the gravitational well. From their point of view, you never quite cross the event horizon. You fade, you slow, you approach endlessly, but you do not disappear in any finite amount of time. It is as if the universe refuses to show them the final step. And yet, from your own perspective, nothing unusual happens to your internal clock. Your watch ticks as it always has. Your thoughts flow at their normal pace. You do not feel yourself slowing. You do not notice any freezing of motion. This difference between perspectives is one of the most fascinating aspects of relativity. Both views are correct, and yet they describe entirely different experiences. While this is happening, the light from the outside universe begins to change in a different way. Looking outward, away from the black hole, you would notice that the rest of the universe appears to speed up. Events that would normally take hours or days seem to unfold more quickly. If you were close enough to the event horizon of a very large black hole, you might, in principle, watch stars evolve, planets orbit, or distant galaxies shift at a noticeably accelerated pace. This is not because time is speeding up for them in an absolute sense, but because your position in the gravitational field alters the relationship between your time and theirs. There is something quietly profound about this. The closer you move to the event horizon, the more disconnected your experience of time becomes from the rest of the universe. You're not just travelling through space anymore, you're moving through a region where time itself is being reshaped, stretched into a new configuration that no longer aligns with the rhythms you have always known. And still, there is no visible line. It is tempting to imagine the event horizon as a boundary you can see approaching, like the edge of a cliff or the surface of water, but it is nothing like that. If you were to extend your hand forward, there would be no sensation, no change in temperature or pressure as it passes the threshold. The laws of physics do not announce this crossing with a dramatic signal. Instead, the significance of the event horizon lies in what becomes impossible afterward, not in what you directly experience at the moment of crossing. At some point, without realizing it, you would cross that boundary. The realization is unsettling, not because anything immediately changes, but because of what it implies. Every path you could take from this moment forward leads inward. Every possible future you have is directed toward the centre. There is no turning around, no slowing down to reconsider. Even if you fired your engines with all available power, even if you could somehow reach speeds approaching that of light, it would not be enough. The structure of space-time itself has shifted in such a way that outward paths no longer exist, and yet you would not feel trapped. This is one of the strangest aspects of the experience. There is no force pushing you inward, no sensation of being dragged or compressed at this exact point. Locally, everything feels the same. You're simply following a path through space-time just as you always have. The difference is that the geometry of that space-time has changed so profoundly that all possible paths now lead deeper into the black hole. Looking back, you would still see the universe behind you, though it would appear increasingly distorted. Light from distant stars would be bent into strange shapes, forming a kind of glowing ring around the black hole. This effect, caused by extreme gravitational lensing, creates the illusion that you can see regions of space that would normally be hidden behind you. The universe wraps itself around your field of view, as though space has folded in on itself. The colours might shift as well. Light climbing out of the gravitational well loses energy, becoming redder and dimmer. Over time, the outside universe would appear darker, its signals stretched into wavelengths that your eyes cannot detect. Eventually, the familiar glow of stars would fade, replaced by a dim, distorted panorama that feels both vast and strangely enclosed. Meanwhile, the blackness ahead is not simply empty. It is not a void in the usual sense. It is a region where paths converge, where every direction leads toward the same ultimate destination. The absence of light is not due to a lack of illumination, but because light itself cannot escape from deeper regions to reach you. You're moving into a domain where visibility is not limited by distance, but by the fundamental structure of space-time. At this stage, the tidal forces we mentioned earlier begin to play a more noticeable role depending on the size of the black hole. For a supermassive black hole, you might still feel relatively comfortable at the event horizon, with only subtle differences in gravitational pull between different parts of your body. For a smaller black hole, however, the stretching effect could already be significant, pulling more strongly on your feet than your head, gradually elongating your form. But even this stretching is not sudden. It builds gradually, a quiet increase in tension rather than a sharp jolt. The universe, even at its most extreme, tends to operate with a kind of continuity, changing conditions smoothly rather than abruptly. There is also a deeper, more abstract shift taking place, one that is harder to visualize. Outside the event horizon, you can choose to move in different directions, forward, backward, sideways, each corresponding to a different path through space-time. Inside the event horizon, this freedom changes in a fundamental way. The direction toward the centre of the black hole becomes as unavoidable as the direction toward the future. Just as you cannot choose to move backward in time, you cannot choose to avoid moving inward once you have crossed this boundary. This idea can feel disorienting at first, It suggests that the structure of reality itself has been rearranged, that what we think of as direction is not fixed, but depends on the geometry of space-time. Inside a black hole, the distinction between space and time becomes blurred in a way that challenges our usual intuition. Moving inward is not just a movement through space, but a progression toward an inevitable outcome, much like moving forward in time, and yet your experience remains calm. You're not overwhelmed by noise or heat or sudden forces. You're simply continuing along a path, observing the changes around you, noticing the distortions in light, the shifting of time, the subtle increase in tidal effects. The drama of the situation exists more in the implications than in the immediate sensations. It is this contrast that makes the approach to the event horizon so fascinating. On one hand, it represents one of the most extreme transitions in the universe, a boundary beyond which escape is impossible. On the other hand, the crossing itself is uneventful, almost quiet, as though the universe is indifferent to the significance we assign to it. This invites a different kind of reflection. Rather than thinking of the event horizon as a dramatic edge, it may be more accurate to think of it as a point of no return in a deeper sense, a shift in the structure of possibilities. Before crossing, there are paths that lead outward, ways to return, options that keep you connected to the rest of the universe. After crossing, those options vanish, not because of a barrier, but because of the way space-time itself is shaped. You are still moving, still experiencing, still observing, but the set of possible futures has narrowed to a single direction. The event horizon is not an endpoint, but a beginning, the start of a region where the familiar rules no longer apply in the ways we expect. Something begins to feel slightly off long before anything looks dramatic. Not in a way that would alarm you, not in a way that forces immediate attention, but more like a quiet inconsistency, the kind you might notice when a clock in a room ticks just a little differently than expected. Everything still works, everything still flows, yet there is a subtle sense that the rhythm of the events is no longer perfectly aligned with what you've always known. Drifting deeper now, with the event horizon already behind you, time becomes less of a steady background and more of an active participant in what you experience. It does not announce itself as changing. There is no moment where you suddenly think, "No, time is different." Instead, the change reveals itself indirectly, through comparisons, through observation, through the quiet realization that what you see and what others would see are no longer the same story. From your own perspective, everything continues normally. Your thoughts arrive at their usual pace. If you were to count seconds, they would feel consistent, one following another in the same familiar rhythm. Your heartbeat, your breathing, even the way you might blink or shift your attention, all of it remains unchanged. This is important because it highlights something subtle but fundamental. Time, as you experience it personally, does not feel distorted. It is only when you compare your time to the rest of the universe that the differences become clear. Looking outward, away from the black hole, the universe begins to behave in a way that feels increasingly unusual. Events appear to speed up. Light from distant stars and galaxies arrives more quickly, compressed into shorter intervals. If you were able to observe something predictable, like the rotation of a distant planet or the pulsing of a star, you would notice that these cycles seem to accelerate. What might take hours or days far away could appear to unfold much faster from your vantage point. This effect grows stronger the deeper you go. The further inward you move, the more compressed the outside universe becomes. It is not that those distant events are actually happening faster in their own frame of reference. They are unfolding as they always have. But because of the extreme curvature of space-time around you, the relationship between your time and theirs is no longer balanced. It is as if you are watching a distant movie that is being played at an increasing speed, not because the film itself has changed, but because your connection to its timing has shifted. Meanwhile, if someone far away were observing you, their experience would be very different. To them, your motion appears to slow dramatically as you approach the event horizon. Even though you have already crossed it from your own perspective, they would still see you hovering near the edge, your movements becoming more and more sluggish, your signals arriving less frequently. There is something quietly fascinating about this duality. Two observers, both experiencing reality correctly from their own point of view, yet describing completely different versions of the same event. It reminds us that time is not a universal constant ticking identically for everyone everywhere. Instead, it is woven into the structure of space itself, shaped by gravity, motion, and position. As you continue inward, another effect begins to layer itself onto this shifting relationship with time. Light from the outside universe does not just appear faster, it also begins to change in colour and intensity. At first, the shift is subtle. Light that would normally appear in familiar colours starts to move slightly toward the blue end of the spectrum. This is known as blue shift, a consequence of falling deeper into a gravitational field. Photons gain energy as they move toward you, their wavelengths shortening, their frequencies increasing. The stars might appear a bit brighter, a bit sharper, their light carrying more energy than before. But this does not continue indefinitely in the same direction. As you move further, and as your ability to receive signals from the outside becomes more limited, the situation begins to reverse in a different sense. From the perspective of the distant universe, the light you emit becomes redshifted. Your signals stretch out, losing energy, becoming longer in wavelength, dimmer, harder to detect. From your own point of view, the outside universe begins to fade, not because it is disappearing, but because the pathways that light must travel to reach you are becoming increasingly distorted. Space itself is bending in such a way that fewer and fewer photons from certain directions can make their way to your eyes. There is a gradual dimming, a quiet reduction in the richness of the visible universe. The stars that once filled your field of view start to concentrate into a smaller region of the sky. Gravitational lensing intensifies this effect, bending light from behind you into arcs that wrap around your perspective. For a while, this creates a strange and beautiful phenomenon, a ring-like structure where the entire visible universe seems compressed into a glowing band. It is not overwhelming, it is not chaotic, it is simply different. Over time, even this ring begins to lose its clarity. The light becomes more distorted, more stretched, less informative. The universe outside feels farther away, not in distance, but in connection. The signals that once defined your sense of place, the steady presence of stars, galaxies, and cosmic background light, begin to fade into something less distinct. And through all of this, your own sense of time remains steady. This contrast is one of the most profound aspects of the journey. You're not experiencing time slowing down. You're not feeling yourself being stretched across moments or compressed into them. Instead, you're observing the rest of the universe behaving differently relative to you. It creates a quiet kind of isolation, not the kind that comes from being alone in a physical space, but the kind that arises when your experience of reality no longer aligns with anyone else's. The outside universe continues, evolving, changing, moving forward, but its connection to your timeline becomes increasingly abstract. There is also a deeper implication hidden within this behavior of time. As you move further inward, the distinction between space and time begins to blur in ways that are difficult to visualize. Outside a black hole, you can choose your direction in space. You can move left, right, forward, or backward. Time, on the other hand, moves in one direction only, from past to future. Inside the event horizon, this distinction changes. The direction toward the center of the black hole becomes as unavoidable as the direction toward the future. Just as you cannot choose to move backward in time, you cannot choose to avoid moving inward. This is not because of a force pushing you, but because of the geometry of space-time itself. Time and space begin to exchange roles in a subtle way. The inward direction becomes something like a timeline, a path that must be followed, not because of choice, but because of the structure of reality. Moving deeper into the black hole is not just a movement through space, it is in a very real sense a movement toward an inevitable future, and yet, even this does not feel dramatic from your perspective. You continue to observe, to think, to experience. The changes around you are gradual, layered, unfolding with a kind of quiet consistency. The universe is not collapsing into chaos. It is revealing a different set of rules, ones that have always existed but only become apparent under these extreme conditions. Returning to the idea of light, there is another subtle effect worth considering. Information itself becomes harder to access. Everything you know about the outside universe depends on signals reaching you, photons carrying information across space. As space becomes more curved, as pathways become more constrained, the flow of information changes. You receive less, and what you do receive is increasingly distorted. This is not just a visual effect, it is a limitation on knowledge. The further inward you go, the less you can know about what is happening outside. Not because events stop occurring, but because the information about them cannot reach you in the same way. The universe beyond the black hole continues, but your connection to it fades. At the same time, from the outside perspective, your own information becomes trapped. Signals you send outward take longer and longer to escape, stretching, weakening, eventually becoming undetectable. To distant observers, you appear frozen at the edge, your last signals fading into redshift, your presence lingering indefinitely without ever quite disappearing. This creates one of the most intriguing paradoxes in physics. From your perspective, you have already crossed the event horizon and continued inward. From theirs, you never quite make it. Two realities, both consistent within their own frames of reference, yet impossible to reconcile into a single unified description. And still, the experience remains calm. There is no sudden rupture in your awareness, no overwhelming sensation of distortion. The changes in time, light, and connection unfold gently, almost quietly, as if the universe prefers to shift its rules gradually rather than all at once. As you continue deeper, the stretching of time relative to the outside world becomes more extreme, the dimming of light more pronounced, the isolation more complete. The universe you once knew does not vanish, but it becomes something distant, compressed, and increasingly abstract. What remains is your immediate experience, your steady sense of time, your continued movement inward. At first, it doesn't feel like anything dramatic is happening to you at all. Your thoughts are steady, your awareness is intact, and if you are not paying close attention, you might even assume that the journey inward is still as gentle as it has been so far. There is no sudden jolt, no sharp signal from your body saying that something extreme has begun. Instead, the change arrives, quietly, almost politely, like a subtle shift in posture that you only notice after a few moments of stillness. The difference begins with gravity, but not in the way we usually think about it. On Earth, gravity pulls on you evenly. Your entire body is drawn downward with nearly the same force, which is why you don't feel yourself being stretched or compressed in any noticeable way. Near a black hole, however, gravity does not behave so uniformly. The strength of the pull changes rapidly with distance, and when those distances become very small relative to the strength of the field, the variation becomes impossible to ignore. Imagine your body aligned so that your feet are slightly closer to the center of the black hole than your head. The difference in distance might be small, perhaps no more than your height, but the difference in gravitational pull between those 2 points can be enormous. Your feet are pulled more strongly than your head, and your head is pulled more strongly than the space just above it. This creates a gradient, a difference in force that acts across your entire body. At first, this gradient might feel like a gentle stretch, a slight tension along your length, not unlike the feeling of reaching upward after waking up or extending your arms after sitting for too long. It is not painful. It is not even particularly alarming. It is simply a sensation that something is pulling a little more at one end than the other. But as you continue inward, that difference grows. The stretching becomes more pronounced, more persistent, less like a temporary sensation, and more like a continuous condition. Your feet are now being pulled with noticeably greater force than your head, and your body begins to respond to that imbalance. You're not being squeezed or crushed in the way one might expect from something as massive as a black hole. Instead, you are being elongated. This is where the term spaghettification comes from. It sounds almost humorous, a light-hearted word for something that is, in reality, a very serious physical process. Objects falling into a black hole can be stretched into long, thin shapes, much like strands of pasta being pulled from both ends. The name captures the visual aspect of the phenomenon, even if it softens the reality behind it. There is another component to this effect that is just as important as the stretching. While your body is being pulled lengthwise, it is also being compressed from the sides. The same gravitational gradient that stretches you along one direction squeezes you along the perpendicular directions. This combination of stretching and compression changes the shape of objects in a very specific way, turning them into elongated forms. What is interesting is that this process does not occur all at once. It builds gradually, following the same quiet pattern we have seen with other effects near the black hole. The forces increase smoothly, without sudden jumps, giving the impression of a slow, continuous transformation rather than an abrupt event. The exact experience depends heavily on the size of the black hole. If the black hole is relatively small, perhaps only a few times the mass of the Sun, the tidal forces become extreme well before you reach the event horizon. In that case, the stretching would begin earlier, and it would intensify quickly. The difference in gravitational pull between your head and your feet would become so large that the structure of your body would struggle to maintain its integrity. For a much larger black hole, one with millions or billions of times the mass of the Sun, the situation is quite different. The event horizon itself is enormous, and the change in gravitational pull over small distances is less severe at that boundary. In such a case, you might cross the event horizon without feeling any significant stretching at all. The spaghettification process would occur later, deeper inside, where the curvature of spacetime becomes more extreme. This difference in scale is one of the more surprising aspects of black holes. The larger the black hole, the gentler the experience at the horizon itself. It's only further in where the curvature tightens that the tidal forces begin to dominate. Returning to the sensation, as the stretching continues, it would begin to affect not just your overall shape, but the internal structure of your body. Every part of you is made of atoms, and those atoms are held together by electromagnetic forces. These forces are incredibly strong at small scales, far stronger than gravity under normal conditions. But near a black hole, the difference in gravitational pull across even tiny distances can become comparable to these forces. When that happens, the bonds that hold matter together begin to feel the strain. At first, the effect is subtle. Molecules may experience slight distortions, bonds stretching just a little beyond their usual range. As the tidal forces increase, these distortions become more significant. The structure of tissues, cells, and eventually molecules themselves is affected by the growing gradient. It is important to note that this is not an explosion or a sudden disintegration. It is a process driven by differences in force, by gradients rather than absolute values. The black hole is not pulling everything apart equally. It is pulling different parts with different strengths, and that difference is what creates the stretching. From your perspective, however, the experience would still feel continuous. There is no clear moment where you could say, now the stretching has begun in earnest. Instead, it is something that increases steadily, becoming more noticeable over time. The same calm awareness that accompanied your earlier observations remains with you, even as the physical effects become more pronounced. There is also a geometric aspect to consider. As space-time itself becomes more curved, the paths that different parts of your body take through it begin to diverge slightly. Your feet and your head are no longer following perfectly parallel trajectories. They are moving along paths that are shaped differently by the curvature, and this contributes to the stretching effect. In a sense, your body is being asked to follow multiple paths through space-time at once, and the result is that it is pulled apart along those paths. Despite the severity of the physics involved, the process retains the same quiet character that has defined the journey so far. There is no noise, no heat in the usual sense, no dramatic visual cue that signals the transformation. It is a silent interaction between gravity and matter, unfolding according to the same principles that govern the motion of planets and stars, only applied at a scale where those principles reveal their more extreme consequences. Looking outward during this process, the universe would continue to appear distorted and dimmed, as described earlier. The external changes in time and light persist, even as the internal changes in your body become more significant. The two processes, one affecting perception and the other affecting structure, occur simultaneously, each reinforcing the sense that you're moving into a region where familiar intuitions no longer apply, and yet there is a consistency to it all. The same laws that describe a falling apple or an orbiting satellite are at work here. There is no new force, no hidden mechanism that suddenly appears. Everything follows from the curvature of space-time and the way matter responds to it. The difference lies only in the intensity, in how strongly those laws are expressed. As the stretching continues, it becomes clear that this is not an isolated effect. It is part of a broader pattern, one that includes the warping of time, the bending of light, and the narrowing of possible paths. Each of these phenomena arises from the same underlying cause, the extreme curvature created by the black hole. The quiet stretch of your body is, in that sense, just another expression of the same principle. It is gravity, not as a simple pull, but as a difference in pull, acting across space, shaping matter in a way that becomes impossible to ignore at these scales. And as this process deepens, as the elongation becomes more pronounced and the internal structure of matter is increasingly affected, the journey continues inward, toward regions where the behavior of space-time becomes even more extreme, and where the question of what you can see. What your eyes begin to register now is no longer something you could compare to any ordinary experience. Not like looking through a window, not like watching a distant horizon, and not even like drifting through open space. The scene does not collapse into darkness all at once, and it does not remain familiar either. Instead, your entire field of view starts to reorganize itself in a way that feels structured, yet deeply unfamiliar. At first, there is still light, not the kind that fills a room or illuminates objects evenly, but scattered, bent, redirected light that arrives from unexpected directions. Stars that were once behind you no longer stay behind you. Because of the extreme curvature of space-time, their light wraps around the black hole, reaching your eyes from paths that would normally be impossible. You're no longer seeing in straight lines, you're seeing along curves. This creates an unusual effect where the universe appears to fold into itself. Regions of space that should be hidden come into view, and areas that once felt distant seem compressed into narrow arcs. If you were to look straight ahead, toward what would once have been empty darkness, you might still see light, not because there is anything glowing there, but because photons from elsewhere have been redirected into your line of sight. There is no single direction that behaves normally anymore. Instead, your surroundings begin to resemble a distorted sphere of light, with patterns that shift as you move, but not in the predictable way you might expect. The geometry of what you see is shaped entirely by gravity, and gravity here is no longer subtle. It is defining every path that light can take. One of the most striking features is the appearance of a bright warped ring surrounding the central darkness. This is not a solid object, but a consequence of light orbiting the black hole before reaching you. Some photons loop around once, others multiple times, creating layers of distorted images stacked on top of each other. It is possible, in theory, to see multiple versions of the same star, each one arriving along a different curved path, each slightly offset, each carrying information from a different moment in time. The result is not chaotic, but it is complex. Your brain, if it were trying to interpret this, would struggle to map what you see onto any familiar spatial layout. Depth becomes ambiguous. Distance loses its meaning. Objects do not appear where they should be, because the idea of should no longer applies in the same way. At the centre of this visual field is the black region itself, the shadow. It is not simply empty. It is the area from which no light can reach you, not because there is nothing there, but because any light emitted from deeper regions cannot escape outward. The boundary of this shadow is not sharp like the edge of a solid object. It is defined by the last paths that light can take to reach you before being pulled inward. This shadow grows as you fall, not suddenly but steadily, occupying more and more of your view. The bright ring around it becomes thinner, more concentrated, as the available paths for light narrow. The rest of the universe, once spread across a wide field, compresses into this ring, like an image being squeezed into a smaller and smaller frame. At the same time, the brightness begins to change. Earlier, you might have noticed a slight increase in intensity due to blue shift, the energy gain of photons falling into the gravitational well. But now, as your ability to receive light from the outside becomes more limited, the overall effect shifts. The available light is concentrated, but it is also more distorted, less evenly distributed. Some regions may appear unusually bright, where multiple paths of light converge. Others become dim, where fewer photons can reach you. The contrast increases, not because the universe itself has changed, but because your position within the curved space-time limits what can be seen and how it arrives. There is also a temporal aspect to what you're seeing. Because light takes time to travel, and because the paths it takes are now longer and more complex, the images you observe are not all from the same moment in any simple sense. You might see light that left a distant star at different times, arriving simultaneously after following different routes around the black hole. This means that what you are observing is not just a distorted version of space, but also a layered version of time. You are, in a very real sense, looking at multiple slices of the universe's history at once, compressed into a single visual field. The distinction between now and then becomes less clear, because the paths that light takes blur those boundaries. Despite all of this complexity, your experience remains continuous. You're not overwhelmed by flashes or rapid changes. The distortions evolve smoothly as you fall, each shift building on the last. The universe does not flicker or jump. It transforms gradually, allowing your awareness to follow the changes without abrupt interruption. Looking outward, the rest of the universe appears increasingly distant, not just in space, but in connection. The ring of light that once contained the stars begins to dim as fewer photons can reach you. The colours may stretch beyond the visible range, shifting into wavelengths your eyes cannot detect. Eventually, the external universe becomes faint, not entirely gone, but reduced to a subtle presence, a memory carried by the last available light. The structure of space-time between you and the outside has become so curved that most paths for light lead inward rather than outward. What remains is a narrowing window through which the rest of reality can still be glimpsed. And then even that begins to fade. The shadow grows larger, occupying more of your field of view, not because it is expanding in any physical sense, but because your position relative to it is changing. You're moving deeper into a region where fewer and fewer light paths escape outward, and more are drawn inward. There is a quiet inevitability to this. No sudden blackout, no dramatic loss of vision, just a gradual reduction in available information. The universe outside does not disappear all at once. It recedes step by step as the geometry of space-time reshapes what can reach you. At this stage, what you see is dominated by the structure of the black hole itself, the central darkness, the thinning ring of distorted light, and the subtle gradients of brightness and colour that reflect the last remaining connections to the outside universe. It is not empty, but it is minimal, a simplified view of reality where only the most persistent signals remain. There is also a sense in which your visual experience becomes more inward focused, not in the sense of looking at yourself, but in the sense that the external reference points that once defined your surroundings are no longer available. Without a clear star field, without stable patterns of light, your perception of orientation becomes less grounded. Up and down lose their meaning, left and right become arbitrary. What remains is a direction of motion, inward, and a field of view that reflects that motion, centered on the region toward which all paths now lead. This is not disorienting in a chaotic way. It is more like a simplification, a reduction of complexity. The universe, which once provided countless points of reference, now offers fewer and fewer, leaving behind a more focused, more constrained visual experience. And yet, even here, there is structure, the curvature of light, the gradients of brightness, the remaining traces of distant signals. All of it follows precise rules. The patterns you see are not random. They are the direct result of the geometry of spacetime, expressed visually through the behavior of light. It is, in a way, a map. Not a map of locations in the usual sense, but a map of how space itself is shaped, how paths bend, how information travels. What you are seeing is the visible imprint of gravity at its most extreme, translated into patterns your eyes can interpret, even if your intuition cannot fully explain them. There is a point during this inward drift where seeing stops feeling like a simple act and starts to feel like a process you are actively part of. Not in the sense that you are controlling it, but in the sense that your position now directly shapes what can be seen at all. Vision is no longer just about light arriving at your eyes. It is about which paths through space-time are still available for light to travel. Earlier, the distortions were noticeable but still relatable. Stars curved, the sky wrapped slightly, familiar patterns stretched into new shapes. Now the situation deepens. The bending of light becomes so dominant that it begins to define the entire visual experience. What you see is less a picture of the universe and more a filtered result of which photons can still reach you. Light, under normal circumstances, travels in straight lines. That assumption is so deeply built into everyday perception that we rarely question it. When you look at an object, you trust that the light from it has taken a direct path to your eyes. Near a black hole, that assumption quietly dissolves. Every photon you receive has followed a curved path, sometimes a very curved one. Some have taken the shortest available route, gently bent by gravity. Others have looped around the black hole one or more times before arriving. A few may have travelled along paths so indirect that they carry information from regions of space that would otherwise be completely hidden from view. This means that a single point of light in your vision might not correspond to a single location in space. It could represent multiple overlapping images, layered together by the geometry of space-time. Your eyes receive the signal, but the meaning of that signal is no longer straightforward. The idea of where something is becomes difficult to define. If you were to point at a bright spot in your field of view and ask where that light originated, the answer would not be simple. It might have come from behind you, curved around the black hole, and arrived from what appears to be in front of you. Or it might represent several different paths, each corresponding to a different trajectory and a different moment in time. The deeper you move, the fewer direct paths remain. Light that once had many possible routes to reach you now finds those routes restricted. Space-time is curved so strongly that most paths lead inward rather than outward. The number of photons that can escape from the outer universe and reach you decreases steadily. This creates a narrowing of vision, but not in the way of closing your eyes or dimming a light. It is more like a gradual filtering, where only certain angles, certain directions still allow light to pass through. The bright ring that formed earlier becomes more prominent for a time, not because it is growing, but because everything else is fading. It acts like a final channel through which the outside universe is still visible. Within that ring, light is concentrated, intensified by the bending of its path, creating regions of brightness that stand out against the growing darkness. Outside that ring, there is less and less to see. The central region, the shadow, expands further across your view. It is not a surface, not something you can focus on in the usual sense. It is the absence of reachable light, the region where all paths for photons lead inward, away from you. This absence is not abrupt. It spreads slowly, occupying more of your vision, as the available routes for light diminish. Meanwhile, the light that does reach you begins to change in energy in more complex ways. Earlier, falling inward meant encountering blue shift, where incoming light gained energy and shifted toward higher frequencies. That effect still exists, but it becomes intertwined with another limitation. Not all light can reach you anymore, and the light that does is shaped by increasingly extreme conditions. Some photons arrive with very high energy, compressed by the gravitational field. Others are stretched along their journey, depending on their path and origin. The overall effect is not a uniform brightening or dimming, but a patchwork of intensities, a visual field where brightness varies depending on how spacetime has guided each individual photon. Colours, if they are still visible, become less reliable as indicators of anything familiar. Light may shift beyond the range your eyes can detect. Some wavelengths stretch into the infrared or even longer ranges, becoming invisible to you. Others compress into higher frequencies, potentially moving into ultraviolet or beyond. What remains in the visible range is only a portion of what is actually there. So even when you are seeing something, you are not seeing all of it. Vision becomes partial, not just because of darkness, but because of the limits of your own perception combined with the distortions of space-time. There is also the question of timing. Photons arriving at your eyes are no longer synchronized in any simple way. Light that left distant objects at different times can arrive together, while light from nearby events may take longer paths and arrive later. The order in which you receive information is no longer tied to the order in which events occurred. This creates a subtle layering of perception. You might see an event that, from another perspective, has already passed long ago. At the same time, you might be missing events that are happening now in some distant region, simply because their light cannot reach you along any available path. The concept of current vision becomes less meaningful. You are seeing what the geometry of space-time allows you to see, not necessarily what is happening at this moment in any universal sense. As you continue inward, the structure of what remains visible simplifies further. The ring of light, once complex and filled with detail, begins to lose resolution. Individual stars blur together, not because they are closer, but because the paths their light takes are increasingly constrained. Fine details are harder to distinguish as fewer photons arrive to carry that information. The outside universe becomes less like a detailed image and more like a fading signal. At some point, the visual field is dominated almost entirely by the central darkness and the faint remnants of light at its edge. The richness of the earlier view, with its layered distortions and overlapping images, gives way to something quieter, more minimal. There is still structure, but it is subtle. Gradients of brightness, slight variations in intensity, faint traces of the ring that once held the universe in view. These are the last visual connections to everything outside the black hole, and through all of this, your act of seeing remains unchanged on the inside. Your eyes function as they always have. Photons strike your retina. Signals travel along your nerves. Your brain interprets them. The biological process continues normally. What has changed is not your ability to see, but what can be seen at all. Vision is limited not by your senses, but by the structure of the space you are in. There is something quietly profound in that. It means that perception is not just about the observer, but about the environment in which observation takes place. The same eyes, the same brain, placed in a different region of space-time, produce an entirely different experience of reality. As the last accessible light fades further, the visual field approaches a kind of stillness. Not complete darkness yet, but a state where change is minimal, where the patterns you see evolve slowly, almost imperceptibly. The dynamic distortions of earlier stages give way to a quieter, more stable configuration, shaped by the limited set of photon paths that remain. At this point, the role of vision itself begins to diminish. There is less new information arriving, fewer changes to track, fewer details to interpret. The journey continues, but what you can see plays a smaller role in defining it. The emphasis shifts gradually from observation to understanding, from what appears in front of you to what is implied by the conditions around you. Because even though the visual field is fading, the physical processes continue. Gravity still shapes your motion. Space-time still curves inward. The structure of the black hole still defines every possible path ahead. It is tempting to imagine that somewhere ahead there must be a clear destination, a final point, a place where everything you have been moving toward finally resolves into something definite. After all, the idea of a black hole often brings with it the image of a center, a core, something hidden deep inside where all paths eventually lead. And that idea has a name, one that appears often in physics, in books, and in conversations about the universe, the singularity. At first, it sounds like a place, a location you could, in principle, point to and say, that is where everything ends up. But as we move deeper into this thought, it becomes clear that the singularity is not quite like any place you have ever known. It is not a surface you can approach in a familiar way. It is not something you could see coming into view, the way you might approach a planet or a star. Instead, the singularity is better understood as a prediction, a result that emerges when we follow the equations of general relativity all the way to their limits. According to those equations, if enough mass is compressed into a small enough region, the curvature of space-time becomes so extreme that it effectively collapses into a point of infinite density. At that point, quantities that we rely on to describe the universe, things like distance, volume, and curvature, stop behaving in any meaningful way. They become undefined or infinite, or both. And this is where the question begins to shift, because when something becomes infinite in a physical theory, it often signals not that reality itself has become infinite in that exact way, but that our current description has reached its limit. It is like following a map to the edge and finding that the map simply ends, not because the world ends there, but because the map can no longer describe what lies beyond. So when we ask whether there is truly a singularity, we're also asking whether our understanding of physics remains complete under these conditions. From your perspective, continuing inward, the idea of a point of no return has already been crossed. That happened at the event horizon. There is no path back outward, no trajectory that leads away from the centre. Every possible future you have is directed inward. But the singularity represents something different. It is not about escape. It is about the ultimate outcome of the path you're on. And even here, things are not as straightforward as they might seem. In everyday thinking, when we imagine moving toward a central point, we picture distance shrinking, space narrowing, and eventually reaching a specific location. But inside a black hole, the structure of space-time changes in such a way that the singularity is not just a place in space. It behaves more like a moment in time. This can feel counterintuitive at first. Outside the black hole, time flows forward, and you cannot choose to stop it or reverse it. It is a direction you're carried along inevitably. Inside the event horizon, the direction toward the singularity takes on a similar character. It is not something you can avoid or move around. It is a direction that is built into the structure of reality in that region. In that sense, Asking whether you will reach the singularity is almost like asking whether you will reach the future. The answer is not about choice, it is about inevitability. And yet, even with this inevitability, the nature of what you are approaching remains uncertain. From the standpoint of general relativity alone, the singularity is a point of infinite density and zero volume. But physics does not end with general relativity. At very small scales, quantum mechanics becomes important, and quantum mechanics does not easily allow for infinities in the same way. This creates a tension between our best theories. General relativity predicts the singularity, while quantum mechanics suggests that something more complex might happen before such a point is ever truly reached. Unfortunately, we do not yet have a complete theory that unifies these two frameworks. This means that the true nature of the singularity is still an open question. It may not be a point in the traditional sense at all. Some ideas suggest that instead of a singularity, there could be a region where matter is compressed to an extremely high but finite density, governed by quantum effects that prevent the formation of true infinities. Others propose that space-time might take on a different structure entirely at these scales, perhaps forming something like a bridge to another region, or a state where the usual concepts of space and time no longer apply. From your perspective, however, the journey continues regardless of which of these possibilities is correct. You're not given a preview of the answer as you approach. There is no visible marker indicating what the singularity really is. The path inward remains smooth in the sense that your experience continues without interruption, even as the underlying physics becomes more uncertain. There is also the question of how long it takes to reach this point. From your own frame of reference, the time to reach the singularity is finite. Depending on the size of the black hole, it could be seconds, minutes, or longer, but it is not infinite. You do not fall forever in your own experience. The path has an endpoint in time, even if the nature of that endpoint is not fully understood. This contrasts sharply with the perspective from outside. To a distant observer, you never appear to cross the event horizon at all. You seem to slow down, fade, and remain near the boundary indefinitely. The idea that you could then continue inward and reach a singularity is not something they would ever directly observe. So once again, there are two descriptions of reality. One in which you move inward, cross the horizon, and eventually reach the center in finite time. Another in which you appear frozen at the edge, never quite completing the journey. Both descriptions are consistent within their own frames of reference, and both arise from the same underlying laws of physics. Returning to the idea of a point of no return, it becomes clear that there are two layers to that concept. The first is the event horizon, where escape becomes impossible. The second is the singularity, where the path itself comes to an end, at least according to our current understanding. Between these 2 points lies the region you are now imagining, a domain where the rules of space and time have shifted, where every step forward is also a step deeper into a question that physics has not yet fully answered. There is something quietly humbling about that. Even with all our equations, observations and theories, there remains a limit to what we can predict with certainty. The singularity represents that limit, not just as a physical concept, but as a boundary of knowledge. And yet, the journey toward it is not chaotic or random. It follows from the same principles that govern everything else we have discussed. The curvature of space-time, the behavior of gravity, the relationship between mass and motion, all of it continues to apply. The difference is that we're now approaching a region where those principles reach their most extreme expression. As you continue inward, the idea of a final point becomes less about a specific location and more about the structure of the path itself. You're moving along a trajectory that cannot be altered, toward a condition that may not be fully describable in the language we currently use. The singularity is not something you can prepare for in a practical sense. It is not something you can observe directly before reaching it. It is something that defines the endpoint of the journey, even if its true nature remains uncertain. And so the question, is there a point of no return, has already been answered once at the event horizon, but it takes on a deeper meaning here. There is not just a boundary you cannot cross back over, there is also a destination you cannot avoid moving toward. Between those two ideas lies the full shape of what it means to fall into a black hole, a path that is both defined and mysterious, predictable in its direction, yet uncertain in its ultimate outcome. Long before anyone imagined falling toward a black hole in this kind of detail, there was a quiet shift in how we understood the universe at all. It did not begin with telescopes pointed at distant galaxies or images of glowing rings in space. It began with questions about light, motion, and how different observers describe the same event. Those questions led Albert Einstein to reshape the foundations of physics, and it is within that framework that everything you're now experiencing starts to make sense. The ideas we rely on here come primarily from what is known as general relativity, a theory that describes gravity not as a force in the traditional sense, but as the curvature of space-time itself. Earlier we used the image of a stretched blanket to describe this curvature, and that image still works, but here the blanket is no longer gently curved. It is pulled into an extreme shape, one that defines every possible path you can take. At this stage of the journey, you're no longer just observing relativity in subtle ways. You're fully inside its most extreme environment, where its predictions are no longer small corrections to everyday experience, but the dominant structure of reality itself. One of the first things to recognize is that space and time are not separate ingredients. They're woven together into a single fabric, and gravity is the way that fabric bends under the presence of mass. When that bending becomes extreme, as it does inside a black hole, the distinction between where and when begins to blur in ways that challenge ordinary intuition. Outside the black hole, you could think of your position in terms of 3 dimensions of space and 1 dimension of time. You could move freely through space, choosing your direction, while time carried you forward whether you wanted it to or not. Inside the event horizon, that balance shifts. The direction inward, toward the center, behaves like time. This is not just a metaphor. In the equations of general relativity, once you cross the event horizon, the coordinate that once represented distance from the center begins to act like a time coordinate. It becomes something you cannot avoid moving along, just as you cannot avoid moving forward in time. This means that falling inward is not something you can choose to stop. Even if you had the ability to move in any direction within your local surroundings, the overall structure of space-time ensures that every possible path leads deeper. It is not that you're being pushed or pulled in a forceful way. It is that the geometry itself allows no alternative, and yet locally everything still feels smooth. This is one of the most important principles in relativity, the idea that in a small enough region of space-time, the laws of physics look normal. This is often called the equivalence principle. If you were in free fall, even inside a black hole, you would not feel a force acting on you in the same way you feel gravity on Earth. You would feel weightless, just as astronauts do in orbit. So while the large-scale structure of space-time has changed dramatically, your immediate experience remains calm and continuous. Looking outward, the distortions we discussed earlier, the bending of light, the compression of the visible universe into a shrinking region, all of that is a direct consequence of how geodesics, the natural paths through space-time, behave in this environment. Light follows these paths, and because the geometry is curved so strongly, those paths wrap, twist, and converge in ways that would be impossible in flat space. Your own path is also a geodesic. You're not being dragged along by a force in the usual sense. You are following the straightest possible path in a curved space-time. It just happens that this path leads inward, toward the region where curvature becomes extreme. There is something quietly elegant about this. Even in the most extreme conditions the universe can produce, motion remains simple at its core. Objects follow paths determined by geometry. Light follows those same principles. The complexity arises not from new rules, but from how those rules play out when space-time itself is no longer flat. Another aspect of relativity that becomes especially important here is the idea of simultaneity. In everyday life, we assume that events happening at the same time for one observer happen at the same time for everyone. Relativity shows that this is not the case, even at moderate speeds. Near a black hole, this difference becomes much more pronounced. Events that appear simultaneous to you may not be simultaneous to someone far away. In fact, the very concept of a shared now becomes difficult to define. Your slice of space-time, the set of events you consider to be happening at this moment, is tilted relative to that of distant observers. This contributes to the earlier effect where you see the outside universe speeding up. It is not just that time is passing differently, it is that your definition of now is no longer aligned with theirs. You're effectively sampling different parts of their timeline as you move inward. From your perspective, the universe outside continues to evolve, perhaps even appearing to race forward. From theirs, your journey appears to slow and stretch out indefinitely. These two descriptions are not in conflict. They are reflections of how different observers move through the same underlying space-time. Relativity allows both to be true. There is also the question of energy and motion. As you fall inward, your velocity relative to distant observers increases. From their point of view, you approach the speed of light as you near the event horizon, but from your own perspective, you are not accelerating in any unusual way. You're simply continuing along your path. This difference arises because velocity itself is relative. There is no absolute frame of reference that everyone agrees on. Each observer measures motion relative to their own state, and near a black hole, these differences become more pronounced. The deeper you go, the more extreme these differences become. The curvature of space-time increases, the separation between different observers' perspectives grows, and the predictions of relativity dominate every aspect of the experience. This is why black holes are often described as natural laboratories for testing general relativity. They provide conditions that cannot be replicated anywhere else, and yet, despite all of this complexity, the theory itself remains consistent. The same equations that describe the orbit of a planet also describe your motion here. The difference is in the scale of the curvature, not in the rules themselves. This continuity is one of the strengths of relativity. It does not require special cases or exceptions. It applies everywhere, from the weakest gravitational fields to the strongest. Still, there is a boundary to its applicability. As you move closer to what we call the singularity, the predictions of general relativity begin to break down. The curvature becomes so extreme that the equations no longer produce meaningful results. This is where the need for a more complete theory, one that combines relativity with quantum mechanics, becomes apparent. But up to that point, relativity provides a remarkably accurate description of what is happening. It tells you why light bends, why time behaves differently, why paths converge inward, and why the experience of different observers can diverge so dramatically. It explains the structure of the black hole not as a mysterious object, but as a region where space-time itself has been shaped into a particular form. There is something reassuring in that. Even in a place that feels so far removed from everyday experience, there is a framework that allows us to describe it, to predict it, to understand it, at least in part. The abyss is not random. It is governed by rules that, while unfamiliar, are consistent and precise. Relativity has carried us this far, explaining how space and time behave under extreme gravity. But there are questions it does not fully answer, especially when we consider what happens to information, to the details of what falls into a black hole and whether anything is truly lost. It doesn't arrive all at once. There is no sudden snap, no sharp dividing line between calm and extreme. Instead, the change begins as something so subtle that it almost feels like a continuation of everything you've already been experiencing, just slightly more noticeable, slightly more persistent. The same quiet pull that has been guiding you inward now begins to reveal a new layer of its behaviour, one that depends not just on how strong gravity is, but on how differently it acts across space. Gravity, as we usually experience it, feels uniform. On Earth, your head and your feet are pulled downward with almost exactly the same strength, which is why you don't feel stretched or distorted. But here, deep within the influence of a black hole, that uniformity no longer holds. The strength of gravity changes rapidly over very small distances, and it is this change, this difference in pull, that defines what are known as tidal forces. At first, the effect is almost gentle. If you imagine yourself aligned so that one part of you is slightly closer to the centre than another, the closer part feels a stronger pull. It is not dramatic yet. It is more like a slight imbalance, a difference that you might only notice if you were paying close attention. Your body is not being crushed or torn. It is simply experiencing a variation, a gradient, in how gravity acts upon it. This is the key idea. Tidal forces are not about how strong gravity is overall. They are about how much gravity changes from one point to another. As you move deeper, that change becomes more pronounced. The difference in pull between your feet and your head increases, not in a sudden jump, but in a steady progression. The same is true for any object around you. A tool, a piece of equipment, even a small particle, all of it experiences slightly different gravitational forces depending on its position. This creates a stretching effect along the direction toward the centre. At the same time, there is a complementary effect across the other directions. While you're being stretched lengthwise, you're also being gently compressed from the sides. This combination is not arbitrary. It follows directly from the way gravity curves space-time, shaping how distances and directions behave. In the beginning, the sensation might still feel manageable. There is tension, yes, but not yet overwhelming. It is similar to the earlier stretching we discussed, but now it becomes clearer that this is not a passing effect. It is a fundamental feature of the region you are in, one that will continue to intensify as you move inward. The scale of the black hole continues to matter here. If this were a very large black hole, the tidal forces near the event horizon would have been quite mild. You might have crossed that boundary without noticing anything unusual at all. But now, as you go deeper, even a supermassive black hole begins to show its more intense side. The curvature of space-time increases, and with it, the differences in gravitational pull. For a smaller black hole, this stage would have arrived much earlier, and with far greater intensity. But regardless of size, the pattern is the same. Gentle at first, then gradually more demanding. The universe does not switch modes abruptly. It evolves conditions smoothly, even when those conditions lead to extreme outcomes. There is something quietly consistent about this progression. The same laws that describe the earlier stages of your approach are still in effect. Nothing new has been introduced. There is no hidden force that suddenly appears. What changes is the scale, the magnitude of the effects that were already present. As the tidal forces grow, they begin to affect not just your overall shape, but the relationships between smaller and smaller parts of matter. Earlier, the stretching was something you could imagine happening across your entire body. Now, it begins to extend into finer scales. The forces acting on different parts of you become more distinct, more difficult for the internal structures of matter to resist. It is important to keep in mind that matter is not held together by gravity alone. Atoms are bound by electromagnetic forces, which are extremely strong at small distances. Molecules, cells, and larger structures all rely on these forces to maintain their integrity. Under normal circumstances, these forces easily dominate over any differences in gravity. But here, the gradient in gravity becomes comparable to those internal forces. That is when the effects become unavoidable. The stretching is no longer just a large-scale deformation. It begins to influence how matter itself holds together. Bonds are strained. Structures are pulled along slightly different paths. and the coherence of larger objects becomes increasingly difficult to maintain. Even so, the process remains continuous. There is no single moment where everything suddenly changes state. Instead, there is a steady increase in the differences between forces, a gradual transition from a situation where matter can hold itself together comfortably to one where those forces are under constant strain. At the same time, your motion through spacetime continues along its predetermined path. You're still following a geodesic, the natural path dictated by the curvature of spacetime. You're not resisting these forces in the way you might resist a push or a pull in everyday life. You are moving with them, carried along by the geometry itself. This is why, even as the tidal forces grow, the experience is not one of sudden impact. There is no collision, no shock wave, no abrupt event. It is a steady interaction, one that becomes more intense but never loses its continuity. Looking outward, the visual field continues to fade, as described earlier. The remaining light is limited, distorted, and increasingly sparse. The universe outside no longer provides a stable reference. What remains is the internal experience, the awareness of how conditions are changing, and the understanding of what those changes imply. There is also a directional clarity that becomes more pronounced. The inward direction, toward the centre, is no longer just a path you are following. It is the only path available. The tidal forces align with this direction, stretching along it, reinforcing the sense that everything is oriented toward a single outcome. In contrast, the sideways directions feel constrained. Compression in those directions limits expansion, guiding everything into a narrower configuration. This combination of stretching and squeezing shapes the behavior of matter in a very specific way, one that reflects the underlying geometry of the black hole. It is not random, it is structured. Every effect you observe can be traced back to the same fundamental principle, the curvature of space-time and how it varies across distance. As the journey continues, the difference between gentle and harsh becomes less about a sudden transition and more about a gradual crossing of thresholds. At first, the forces are small enough that they can be accommodated easily. Then they become noticeable. Then they become dominant. The shift from one regime to another is smooth, but the consequences are significant. This is why tidal forces are often described as the defining feature of falling deeper into a black hole. They represent the point at which the abstract idea of curved space-time becomes something that directly affects the structure of matter, something that can no longer be considered purely theoretical, and yet, even here, the universe remains consistent. There is no chaos in the equations, no breakdown in the underlying logic. The same relationships between mass, distance, and curvature continue to apply. The difference is that you are now in a region where those relationships produce their most extreme outcomes. As the stretching increases and the compression tightens, the journey moves further into a domain where the effects of gravity are no longer just something you observe, but something that defines every aspect of what is happening. From far away, the story looks completely different. Imagine someone watching this entire process unfold from a safe distance, perhaps orbiting far beyond the reach of the black hole's strongest pull, their instruments steady, their clocks ticking normally. To them, nothing about your experience feels immediate or continuous. Instead, what they see unfolds in a way that seems slow, stretched, and increasingly incomplete. At first, your motion appears ordinary. You drift closer, accelerating gently, just as any object would when moving toward a massive body. Your path curves inward, your speed increases, and everything follows expectations. If they were tracking you with a telescope, your position would change predictably, your signals arriving at regular intervals. But as you approach the region near the event horizon, something begins to change. Your movement appears to slow, not because you're actually reducing speed in your own frame of reference, but because the light carrying information about your motion takes longer to escape the gravitational field. Each signal you send outward, whether it is a pulse of light, a radio transmission, or simply reflected starlight, must climb out of a deeper and deeper gravitational well. That climb takes time, and more importantly, it takes increasingly more time for each successive signal. To the distant observer, this creates the impression that your motion is stretching out. The intervals between your movements appear longer. Your approach to the event horizon becomes slower and slower, as though you are easing toward it but never quite arriving. This effect is not subtle from their perspective. The closer you get, the more dramatic the slowing appears. Your clock, if they could see it, would seem to tick more slowly. A second for you would correspond to multiple seconds for them, then minutes, then even longer spans as you approach the boundary. This is gravitational time dilation, but seen entirely from the outside. From their point of view, time near the black hole is running slower than time far away. And because you are moving into that region, your entire experience appears to slow down relative to theirs. At the same time, another effect becomes visible. The light coming from you begins to change. As your signals climb out of the gravitational field, they lose energy. This causes the light to shift toward longer wavelengths, a process known as gravitational redshift. Colours that might once have been visible begin to fade toward red, then into infrared, and eventually beyond what their instruments can detect. To them, you're not only slowing down, you're also dimming. Your image becomes fainter, less distinct, as fewer photons reach them, and those that do arrive carry less energy. The combination of time dilation and redshift creates a very specific visual effect. You appear to freeze near the event horizon, your motion stretched out, your signals fading, your presence lingering at the edge without ever quite disappearing. From their perspective, you never cross the event horizon. This is one of the most counterintuitive aspects of black holes. No matter how long they watch, no matter how sensitive their instruments become, they will never see you past that boundary. Instead, you asymptotically approach it, getting closer and closer, but always taking longer to make the next step. Your final signals take an infinite amount of time to reach them. In practical terms, this means that after a certain point, they simply stop receiving useful information. The signals become too weak, too stretched, too infrequent to detect, but in principle your image remains there, suspended near the edge, a fading imprint of your presence. Meanwhile, from your perspective, everything has continued normally. You have already crossed the event horizon, you have moved inward, you have experienced changes in time, light, and structure. The idea that you are somehow frozen at the boundary does not match anything you feel or observe. This creates a situation where two observers describe the same event in completely different ways. One sees a smooth, continuous journey inward. The other sees an object that slows, dims, and never quite crosses the threshold. Both descriptions are correct within their own frames of reference. This is not a contradiction in the theory. It is a consequence of how space-time behaves under extreme gravity. Relativity allows for different observers to measure time and events differently, as long as each description is internally consistent. The key is that there is no single, universal timeline that everyone agrees on. Each observer has their own measure of time, their own sequence of events, shaped by their position and motion within space-time. For the distant observer, your story effectively ends at the event horizon. They cannot see what happens beyond it, not because events stop occurring, but because the information about those events cannot reach them. The event horizon acts as a boundary for communication, not a physical surface that blocks motion, but a limit on what signals can escape. Everything you do after crossing it is hidden from their view. This has an interesting consequence for how black holes are described externally. From the outside, a black hole appears to grow as it absorbs matter and energy, but the process of absorption is never seen directly. Objects seem to approach the horizon and fade away, contributing their mass to the black hole without ever visibly crossing the boundary. It is as though the black hole accumulates information without revealing the final step of how that information is incorporated. This leads to deeper questions about what happens to that information. If an object never appears to cross the event horizon from the outside perspective, then where does its information go? How is it stored? Is it somehow encoded at the boundary itself? These questions connect to some of the most complex ideas in modern physics, but from the observational point of view, the situation remains clear. The event horizon is a one-way limit for signals. Information can enter, but it cannot leave. Returning to the visual experience of the distant observer, there is a quiet stillness to what they see. You appear suspended, your final moment stretched into an endless approach. The dynamic motion that you experience inward is replaced by a static image, slowly fading, losing detail, becoming less and less connected to the present. If they were to wait long enough, your image would effectively disappear, not because you have moved away, but because the signals have become too weak to detect. What remains is the black hole itself, defined by its mass, its influence on surrounding objects, and the absence of any further information from what has fallen in. From their perspective, the black hole is a boundary of knowledge. They can measure its effects, observe its interactions with nearby matter, and detect the gravitational waves produced when it merges with another black hole. But they cannot see inside. They cannot observe what happens beyond the event horizon. This limitation is not due to a lack of technology. It is a fundamental property of the structure of space-time. No matter how advanced their instruments become, no signal from inside the event horizon can reach them. The information is not just hidden, it is causally disconnected from their region of space-time, and yet from your perspective, the journey continues. You are not frozen. You are not fading. You are moving, observing, experiencing. This duality, this separation between perspectives, is one of the most striking features of black holes. It shows that reality is not a single, unified picture that everyone shares. Instead, it is a collection of perspectives, each shaped by position, motion, and the structure of space-time. As the distant observer watches your image fade, their understanding of your journey stops at the horizon. Even before anything looks especially unusual, something fundamental has already started to shift in a way that you cannot feel directly. You're still thinking at the same pace. Your awareness is steady. If you had a clock in front of you, its hands would move exactly as you expect. 1 second follows another without hesitation, without stretching, without interruption. From your own point of view, nothing about time itself seems broken or distorted, and yet everything about time has changed. This is the quiet nature of time dilation. It does not arrive as a sensation. It does not produce a feeling of slowing down or speeding up. Instead, it reveals itself only through comparison, through the relationship between your time and the time experienced elsewhere. Earlier we touched on how a distant observer sees you slow down as you approach the black hole. Now, it becomes useful to look at that same idea from a more personal angle, not just as something they observe, but as something that defines how your aging unfolds relative to the rest of the universe. Because time dilation is not just about clocks, it is about everything that depends on time, which means it is about change itself. Aging at its core is a process measured by time. Cells divide, chemical reactions occur, structures evolve. All of these processes follow the passage of time in your local frame. If your time runs differently relative to someone else's, then your aging runs differently as well. Near a black hole, this difference becomes extreme. From your perspective, you continue aging normally. Your body follows its usual processes. There is no internal signal that your aging has slowed or accelerated. You do not feel younger or older in any unusual way. You simply continue forward, moment by moment. But compared to someone far away, your aging is no longer synchronized with theirs. If they could observe you closely, they would see your movements slow, your actions stretch out, your biological processes unfold more slowly relative to their own time. A heartbeat for you might correspond to many heartbeats for them. A minute for you might correspond to hours, days, or more, depending on how deep you are in the gravitational field. This is not an illusion. It is a real difference in how time passes for different observers, and the deeper you go, the greater this difference becomes. Near the event horizon, the effect is already significant. Your time is running slower relative to the outside universe. As you move further inward, that difference grows even larger. The outside universe appears to accelerate from your perspective, while from theirs, you appear to slow down even more. This creates a kind of separation, not in space, but in time. You are still connected to the rest of the universe, in the sense that you can, for a while, receive signals from it. But your timeline is no longer aligned with theirs. You're moving along your own path through time, one that diverges more and more from everything outside. If you could somehow compare ages directly, the difference would be striking. Imagine two identical clocks, one remaining far from the black hole, the other following your path inward. As time passes, the clock with you would show less elapsed time than the one far away. The difference would start small, then grow larger, and eventually become enormous. This is not because your clock is malfunctioning. It is because time itself is behaving differently in your region of space-time. The same principle has been observed on much smaller scales. Clocks placed at different altitudes on Earth tick at slightly different rates due to the difference in gravitational potential. Satellites in orbit experience time differently than clocks on the ground, and these differences must be accounted for in systems like GPS. What you are experiencing is the same effect, but taken to its extreme limit. Near a black hole, gravity is so intense that the difference in time flow becomes dramatic, not just measurable with precise instruments, but conceptually transformative. From your point of view, the outside universe is moving forward faster. Events unfold more quickly. Processes that would normally take long periods appear compressed. If you could observe distant systems, you might see changes occurring at an accelerated pace, not because those systems have changed, but because your own time has slowed relative to theirs. This creates an unusual situation. You are, in a sense, moving into the future of the universe at a faster rate than someone far away, even though your own experience feels normal. At the same time, from the outside perspective, you are effectively falling out of sync with the present. Your image lingers near the event horizon. Your signals arrive more slowly. Your actions appear stretched out. To them, it is as though you are being left behind in time, even though you are continuing forward in your own frame. This dual interpretation highlights something important. Time is not a universal background that everyone shares equally. It is a local property, shaped by gravity and motion, experienced differently depending on where you are and how you move through space-time. There's also a deeper consequence of this, because aging depends on time, and time depends on your position in the gravitational field. Aging itself becomes relative. You and a distant observer no longer agree on how much time has passed. If, hypothetically, you could return and compare notes, you would find that less time has passed for you than for them. You would have aged less. This idea is often illustrated with thought experiments involving twins, where one travels at high speed or into a strong gravitational field and returns younger than the other. In the case of a black hole, the effect is far more extreme. But there is an important distinction here. While it is possible in principle to return from high-speed journeys and compare ages, it is not possible to return from inside a black hole. Once you have crossed the event horizon, there is no path back to make that comparison directly. So the difference in aging becomes something that exists in theory, something that can be described and understood, but not directly experienced in both directions. You continue aging normally from your own perspective. The outside universe continues aging normally from its perspective. But the relationship between those two timelines diverges in a way that cannot be reconciled by a single shared clock. There is also a limit to how far this comparison can go. As you move deeper, your ability to receive information from the outside decreases. The signals become weaker, more stretched, less frequent. Eventually, the connection fades to the point where the outside universe is no longer part of your immediate experience. At that stage, the idea of comparing aging becomes abstract. You no longer have access to the reference points that would allow you to see how much time has passed elsewhere. Your experience becomes entirely local, defined by your own timeline and the conditions around you. And yet, the underlying principle remains. Your time has been shaped by gravity. Your aging has followed a different path than it would have in a weaker gravitational field. Even though you cannot step outside your own experience to measure it directly, the difference is real, embedded in the structure of space-time itself. There is something quietly profound in this. It means that time is not just something that happens uniformly to everything. It is something that responds to the universe, that changes depending on where you are and how you move. Near a black hole, this becomes undeniable. The idea of a single shared present dissolves. Aging becomes a local process, tied to your path through space-time. The flow of time is no longer something you can assume is the same everywhere. And as this realization settles, it opens the door to deeper questions. If time can behave so differently under extreme gravity, what happens when we consider even smaller scales, where quantum effects begin to matter? How does the structure of space-time interact with the behavior of particles and information at those scales? There is a quiet point in this journey where the explanation we have been following begins to feel complete, almost too complete. The curvature of space-time explains your motion, the bending of light explains what you see, and time dilation explains how your experience separates from the rest of the universe. Everything fits together with a kind of steady logic. And then, almost gently, that certainty starts to loosen, not because anything you have learned becomes wrong, but because it becomes incomplete. Up to now, everything has been guided by the framework of general relativity, the theory that describes how gravity shapes space and time. It works beautifully on large scales, especially in extreme environments like black holes, but there is another layer of physics, one that operates on the smallest scales imaginable, where particles do not behave like tiny solid objects, but more like probabilities, patterns, and possibilities. This is the domain of quantum mechanics. At first, it might seem like these two frameworks should fit together naturally. After all, they are both describing the same universe. But when you bring them into the same place, especially somewhere as extreme as the interior of a black hole, they begin to disagree in subtle but important ways. Relativity treats space-time as smooth and continuous, like a perfectly stretched fabric. Quantum mechanics, on the other hand, suggests that at very small scales, reality is not smooth at all. It is granular, uncertain, and governed by probabilities rather than exact paths. For most situations, this difference does not cause problems. If you are studying planets, stars, or even galaxies, general relativity provides an accurate description. If you're studying atoms, electrons, or photons, quantum mechanics takes over. The two theories operate in their own domains, each successful in its own way. But inside a black hole, those domains overlap. You're now in a region where gravity is extremely strong, and distances are becoming extremely small at the same time. This is exactly where both theories should apply, and exactly where they begin to conflict. This is why black holes are not just objects of curiosity. They are places where our understanding reaches its limits. From your perspective, nothing dramatic announces this shift. You are still moving inward. The stretching of space-time continues. The effects we have described remain in place. But the closer you get to the central region, the more the predictions of general relativity begin to approach those problematic infinities, the singularity we discussed earlier. Quantum mechanics does not easily accept those infinities. In the quantum view, particles do not occupy precise points. They exist in states described by wave functions, spread out over regions, influenced by uncertainty. The idea of compressing everything into an infinitely small point with infinite density does not sit comfortably within that framework. So something has to give. Either our understanding of gravity changes at these scales, or quantum mechanics behaves differently under such extreme conditions, or both theories need to be replaced by a deeper, unified description that we have not yet fully developed. From your position, however, you do not see equations breaking down. You do not observe infinities directly. What you experience is still smooth, continuous, and guided by the same overall structure. The tension between these theories exists in how we describe what is happening, not in how you feel it unfolding moment by moment. There is a subtle shift, though, in how we think about what is real. In quantum mechanics, the concept of certainty becomes less absolute. Instead of exact positions and exact trajectories, we deal with probabilities. A particle does not have a single well-defined path. It has a range of possible paths, each with a certain likelihood. Now consider how that idea might apply here. Your path into the black hole has been described as a geodesic, a well-defined trajectory through curved space-time. But at the smallest scales, that path might not be perfectly sharp. There could be a range of possible micropaths, slight variations that are indistinguishable at larger scales but become relevant when distances shrink enough. This does not change the overall direction of your motion. You're still moving inward. But it suggests that at the deepest level, the structure of reality may not be as rigid as it appears from a purely relativistic perspective. There is also the question of what happens to information. In classical physics, information about a system, its position, its motion, its properties, is preserved. Even if you cannot easily access it, it is still there in principle. Quantum mechanics reinforces this idea in a different way, suggesting that information cannot simply disappear. But a black hole seems to challenge that. If something falls in and can never send information back out, what happens to the details of that object? Are they lost forever, or are they somehow encoded in a way we do not yet fully understand? This question becomes known as the information paradox, and it sits right at the intersection of relativity and quantum mechanics. From your perspective, as you continue inward, nothing about your own information feels lost. You still have your thoughts, your awareness, your structure, at least for now. The laws governing your immediate experience continue to operate. But from the outside perspective, your information becomes inaccessible, trapped beyond the event horizon. Quantum mechanics suggest that this information should not simply vanish. So, where is it? Some ideas propose that the information is somehow stored at the boundary of the black hole, encoded in ways that are not immediately obvious. Others suggest that it might be released very slowly over time through subtle processes associated with the black hole itself. But none of these ideas are fully confirmed. They are attempts to reconcile two powerful theories that both work extremely well in their own domains, yet do not fully agree when brought together here. There is also the concept of quantum fluctuations. At very small scales, empty space is not truly empty. It is filled with temporary changes in energy, particles appearing and disappearing in pairs, a constant subtle activity that never fully settles down. Near a black hole, these fluctuations can have observable consequences. They're connected to phenomena like Hawking radiation, where black holes are predicted to emit tiny amounts of radiation over extremely long timescales. This suggests that black holes are not completely black, but slowly lose energy, a process that ties together quantum mechanics, gravity, and thermodynamics. From your current position, however, these effects are not something you would directly notice. They occur at scales and intensities far removed from your immediate experience, but they are part of the deeper structure of what is happening, part of the underlying reality that governs how black holes behave over time. There is a quiet shift in perspective here. Up to this point, we have been able to describe everything in terms of clear, continuous processes. Now, we begin to acknowledge that at the deepest level, those processes may be underpinned by something less definite, something governed by probabilities, uncertainties, and interactions that do not fit neatly into a single unified picture. And yet, your journey continues without interruption. You do not feel the uncertainty in the way a physicist might describe it. You experience a smooth progression inward, guided by the curvature of space-time. The quantum layer exists beneath that experience, influencing it in ways that are subtle and indirect. There is something almost reassuring about that. Even though our theories are incomplete, even though there are questions we cannot yet answer, the universe still behaves in a coherent way. The large-scale structure remains consistent, the path forward remains defined, and the experience remains continuous. At the same time, the presence of these unanswered questions adds depth to the journey. It reminds us that what we're describing is not the final word, but an evolving understanding, one that continues to grow as we explore further. It begins with a simple question, the kind that feels almost obvious at first, and yet becomes more complicated the longer you sit with it. When something falls into a black hole, does it truly disappear? Up to now, everything you have been imagining has followed a consistent path. You moved inward, crossed the event horizon, continued deeper, experiencing the stretching of space, the bending of light, and the shifting of time. From your perspective, nothing has abruptly vanished. The journey has been continuous, but from the outside, the story looks very different. A distant observer never sees you fully cross the event horizon. Your image slows, fades, and becomes increasingly redshifted until it effectively disappears from view. From their perspective, it is as if you are suspended at the edge and then gradually lost, not through a sudden event, but through an endless fading. This difference in perspective leads directly to a deeper puzzle. In physics, especially within quantum mechanics, there is a principle that information is preserved. This does not mean that information is easy to retrieve, or that it remains in an obvious form, but it does mean that the complete description of a system in principle is never destroyed. If you burn a piece of paper, the information written on it is not truly gone. It is scrambled, dispersed into heat, light, and the motion of particles. But if you could track every detail perfectly, you could, in theory, reconstruct what was written. This idea is known as unitarity, and it is one of the foundational assumptions of quantum mechanics. Now consider what happens with a black hole. You, along with everything you carry, your structure, your motion, your information, crosses the event horizon. From your perspective, all of that information continues inward, but from the outside that information becomes inaccessible. No signal can escape to tell the rest of the universe what has happened. At first glance, this seems like a contradiction. If the information cannot escape, and if the black hole eventually evaporates over an incredibly long time through processes like Hawking radiation, then what happens to the information that fell in? Does it remain trapped forever? Does it get destroyed? Or does it somehow return to the universe in a different form? This is what is called the information paradox. It arises because two very successful theories, general relativity and quantum mechanics, appear to give different answers to the same question. General relativity suggests that anything crossing the event horizon is effectively lost to the outside universe. The information is still there inside, but it cannot influence anything outside. Quantum mechanics, on the other hand, suggests that information cannot be lost at all. Both frameworks work extremely well in their respective domains, yet here they seem to disagree. From your perspective, inside the black hole, nothing about your information feels lost. You still have structure, at least for now. The processes that define your state continue to unfold. There is no moment where you experience a sudden erasure, no instant where everything that defines you simply disappears. The paradox does not exist in your immediate experience. It exists in how different observers describe what has happened. From the outside, the black hole appears to absorb information without returning it. Over time, as the black hole emits Hawking radiation, it slowly loses mass and energy. Eventually, if left undisturbed, it could evaporate completely. If that radiation carries no information about what fell in, then the information would be gone from the universe. But quantum mechanics strongly resist that idea, so physicists have proposed several possibilities. One idea is that the information is somehow encoded in the radiation itself, in a very subtle and complex way. The radiation might appear random at first glance, but if you could analyze it with perfect precision, you might find that it contains correlations, patterns that reflect the information that fell into the black hole. In this view, the information is not destroyed. It is scrambled, spread out over an enormous number of particles, and released slowly over time. Another idea suggests that the information is stored at the event horizon itself, not inside the black hole in the traditional sense, but on its boundary. This concept is related to what is sometimes called the holographic principle, where the information about a volume of space can be encoded on its surface. In that picture, the event horizon is not just a passive boundary. It is an active region where information is preserved, even if it cannot be directly accessed by someone inside. There are also more radical proposals. Some suggest that the interior of the black hole and the exterior description are not separate in the way we usually think, that the information is both inside and encoded outside depending on how you describe the system. Others explore the idea that our understanding of spacetime itself needs to change at a fundamental level, that the paradox is a sign that we are missing a deeper layer of reality that would resolve the contradiction. From your current position, none of these possibilities are directly observable. You do not see information being encoded or decoded. You do not perceive any mechanism that stores or releases it. The journey inward continues, governed by the same curvature of space-time we have been following. And yet, the question remains present. What happens to the details of everything that falls in? Not just large objects, but the exact arrangement of particles, the precise state of matter and energy. Does the universe keep track of all of it, even in a form we cannot easily recognize? Or is there a sense in which information truly does disappear? There is something quietly profound about this uncertainty. It suggests that even at the most extreme edges of our understanding, there are questions that do not yet have definitive answers. The black hole becomes not just a physical object, but a boundary of knowledge, a place where our theories reach their limits. At the same time, the paradox does not mean that the universe is inconsistent. It means that our descriptions are incomplete. General relativity gives us one perspective, one that works perfectly for describing large-scale structure and motion. Quantum mechanics gives us another, one that governs the behavior of particles and information. The challenge is to find a way to bring these perspectives together. As you continue inward, the paradox remains in the background. It does not interrupt your experience, it does not change the path you're on, but it shapes how we think about what is happening, how we interpret the journey, and what it means in a broader sense. Because if information is preserved, then everything that falls into a black hole remains part of the universe in some form, even if that form is hidden, encoded, or delayed. And if it is not preserved, then something about our understanding of physics must change. Either way, the black hole is not just a destination, it is a question, a place where the structure of reality challenges our assumptions, where the familiar ideas of loss and preservation are no longer straightforward, and where the answer depends on a deeper understanding that we are still working toward. Not everything about a black hole is completely silent. For a long time, they were thought to be perfectly one-sided, objects that could only take and never give anything back. Once something crossed the event horizon, that was the end of the story, at least from the outside. No light escaped, no information returned, no signal ever made its way back out. But then a subtle idea emerged, one that changed that picture in a very quiet but very important way. It came from Stephen Hawking, who asked a question that seemed almost simple at first. What happens when you consider the effects of quantum mechanics right at the edge of a black hole? Because while general relativity describes the large-scale structure of space-time, quantum mechanics tells us that empty space is not truly empty. Even in what we would normally call a vacuum, there is activity. Pairs of particles and antiparticles can briefly appear and disappear, borrowing energy from the surrounding space for a very short time before annihilating each other and returning that energy. These are known as quantum fluctuations, and they happen everywhere, all the time, usually without any lasting effect. But near a black hole, something slightly different can occur. Imagine one of these particle pairs forming right at the edge of the event horizon. Under normal conditions, the two particles would quickly come back together and cancel each other out. But if they form in just the right way, one particle can fall inward while the other escapes outward. The pair is separated before they have a chance to recombine. From the outside perspective, it looks as though a particle has been emitted from the black hole. The escaping particle carries energy away, and because energy and mass are related, this means that the black hole loses a tiny amount of mass in the process. This is what we call Hawking radiation. It is not a burst of light or a dramatic release of energy. It is incredibly faint, almost imperceptible for large black holes. The larger the black hole, the weaker this radiation becomes. For something like a supermassive black hole, the effect is so small that it would be completely overwhelmed by other sources of energy in the universe. But the key point is that it exists at all. A black hole is not entirely closed. It can, in a very slow and subtle way, give something back. From your perspective inside, however, nothing about this process feels like an escape. You are still moving inward. The structure of space-time still directs every possible path toward the centre. There is no sensation of particles leaving, no indication that anything is reversing the overall flow. Hawking radiation is something that appears in the description of the black hole from the outside. It is part of how the black hole interacts with the rest of the universe over extremely long timescales. If you could somehow observe the black hole from afar, you would see it gradually losing mass, not through any visible emission like a star, but through this faint, continuous release of energy. Over time, an incredibly long time, the black hole would shrink. The rate of this process depends on the size of the black hole. For small black holes, the radiation is stronger, and they would evaporate more quickly. For large ones, the process is so slow that it would take far longer than the current age of the universe for any noticeable change to occur. Eventually, though, if nothing else falls in, the black hole could evaporate completely. This idea connects directly to the question we explored earlier about information. If a black hole can slowly radiate energy and eventually disappear, then what happens to everything that fell into it? Is the information carried out in the radiation, or is it lost as the black hole shrinks? Hawking's original calculation suggested that the radiation is purely thermal, meaning it does not carry detailed information about what fell in. If that were true, then the information would indeed be lost when the black hole evaporates. But this leads back to the same paradox. Quantum mechanics suggests that information should be preserved, not destroyed. So the existence of Hawking radiation makes the question even sharper. If black holes can evaporate and if information cannot be lost, then the radiation must in some way contain that information, even if it is encoded in a form that is extremely difficult to recognize. This is still an open question. Physicists have proposed many possible resolutions, but there is not yet a single, universally accepted answer. Some ideas suggest that the radiation becomes subtly correlated over time, gradually revealing the information. Others suggest that new physics comes into play near the end of the evaporation process. From your current position, none of this changes the immediate experience. You are not escaping. You are not losing mass in a way you can perceive. The inward journey continues as before, shaped by the curvature of space-time. Hawking radiation is not something you feel. It is something that happens at the boundary, at the edge, where quantum mechanics and gravity meet. There is something quietly interesting about that. The most extreme object we've been describing, one that traps light and defines a region of no return, is not completely isolated. It still participates in the broader universe, still interacts with it, still evolves over time, even if that evolution is incredibly slow. It is not a perfect absorber. It is part of a larger system, and this brings a different perspective to the idea of falling into a black hole. From the inside, the journey feels one way, continuous, inevitable. From the outside, the black hole itself is not static. It changes, it emits, It slowly evolves, even if those changes are almost impossible to notice on human timescales. There is a kind of balance here. On one hand, the black hole represents a limit, a boundary beyond which information cannot return directly. On the other hand, it is not completely sealed. It leaks, very slightly, through quantum processes that connect it back to the rest of the universe. This dual nature reflects the deeper tension between general relativity and quantum mechanics. Relativity gives us the structure of the black hole, the event horizon, the inward flow of space-time. Quantum mechanics introduces fluctuations, uncertainties, and the possibility of emission. Together they suggest that the black hole is not just an endpoint, but a dynamic system, one that continues to evolve even after everything has fallen in. If you step back, not physically, but in the way you think about what a black hole represents, it starts to feel less like an endpoint and more like a record. Not a record you can open and read, not something neatly organised with labels and timestamps, but a record in the sense that everything that has fallen in contributes to what the black hole becomes. Its mass, its rotation, even the way it interacts with its surroundings, all of it reflects a long history of encounters, mergers, and accumulated matter. A black hole does not remember in the way a human mind does. It does not store images, experiences, or narratives, but it carries information in a different form, one that is expressed through a small set of measurable properties. In classical physics, a black hole can be described by just a few numbers: its mass, its spin, and its electric charge. This idea is often summarized by the phrase that black holes have no hair, meaning they do not preserve the detailed features of what formed them, and yet that simplicity hides a deeper story. Every bit of matter that has crossed the event horizon has added to those properties. A star collapsing into a black hole, gas spiraling inward over millions of years, even the merger of two black holes, all of these events leave their mark, not in detailed structure, but in the overall characteristics of the object. The mass increases, the spin changes, the shape of space-time around the black hole adjusts accordingly. From the outside, this is how the history is told. Astronomers observe the motion of stars orbiting a black hole, the behaviour of gas in accretion disks, the emission of jets that can stretch across entire galaxies. These observations allow them to infer how massive the black hole is, how quickly it is spinning, and how it has grown over time. In that sense, a black hole becomes a kind of storyteller, not through words or images, but through its influence on everything around it. Consider a supermassive black hole at the centre of a galaxy. It may have formed from the collapse of an early generation of stars, then grown by absorbing gas, dust, and even other black holes. Over billions of years, it shapes the structure of the galaxy itself. Stars orbit under its influence. Gas clouds are heated and accelerated. In some cases, powerful jets of particles are launched from the regions near the event horizon, affecting star formation far beyond the immediate vicinity. All of this is part of its story. You cannot see the individual events that led to its current state, but you can see the outcome, the accumulated effect of everything that has happened. From your current perspective, inside the black hole, this idea takes on a different tone. You are now part of that story, not in a symbolic sense, but in a literal one. Your mass, your energy, your motion, all of it contributes to the overall properties of the black hole. You are not distinguishable as an individual object from the outside perspective, but the fact that you have fallen in changes the black hole in a measurable way. Its mass increases by a tiny amount. Its energy content adjusts. If you carried angular momentum, that could influence its spin, even if only by an almost imperceptible amount. This is how black holes remember, not by preserving details, but by integrating everything into their overall state. And yet, this raises an interesting tension. Earlier, we discussed the information paradox, the question of whether the detailed information about what falls into a black hole is preserved or lost. If black holes only retain these simple properties, Then it seems as though all the fine details are erased. But quantum mechanics suggests that information should not disappear. So there may be a deeper layer to this story. Perhaps the information is not gone, but encoded in ways that are not immediately visible. Perhaps it is stored in subtle correlations, in the structure of the event horizon, or in the radiation emitted over time. From your position, however, none of this is directly observable. You do not see your own history being recorded. You do not perceive the black hole updating its properties as you fall inward. The process is smooth, continuous, and without any visible bookkeeping, and yet it is happening. The black hole is changing, however slightly, as a result of your presence. There is also a broader perspective to consider. Black holes do not exist in isolation. They are part of a larger cosmic network, interacting with their environments, influencing the evolution of galaxies, and even contributing to the large-scale structure of the universe. When two black holes merge, for example, they produce gravitational waves, ripples in space-time that travel across the universe. These waves carry information about the masses and spins of the merging objects, allowing distant observers to reconstruct aspects of the event. In this way, black holes communicate their history, not directly, but through the effects they produce. Even the growth of a black hole over time leaves traces. The way it accretes matter, the patterns of radiation from its surroundings, the motion of nearby stars, all of these provide clues about what has happened in its past. It is a different kind of storytelling, one that requires interpretation, measurement, and careful analysis. But it is storytelling nonetheless. From inside, the experience remains focused on the present. You're still moving inward, still following the path defined by the curvature of space-time. The idea that you're contributing to a larger narrative does not change what you feel or see in the moment, but it adds context. It places your journey within a much larger framework, one that extends far beyond this single fall. You are part of a process that has been unfolding for billions of years. The black hole you're inside may have formed long before your existence, grown through countless interactions, and will continue to evolve long after this moment. Your contribution is small in scale, but it is not meaningless. It becomes part of the total, part of the accumulated mass and energy that define the black hole's identity. And from the outside, even if your individual story is not visible, the effects of everything that has fallen in are still there, encoded in the properties of the black hole and its influence on the surrounding universe. This perspective shifts the way we think about disappearance. Falling into a black hole does not simply erase something from existence. It transforms it, integrates it into a larger system, where it continues to have effects, even if those effects are not immediately recognizable as coming from any specific source. There is a kind of continuity in that. Not the continuity of personal experience, but the continuity of physical influence. Matter and energy are not destroyed. They are redistributed, reconfigured, woven into the structure of the black hole and its environment. At some stage in this inward path, the idea of strong gravity stops being a useful description. Not because gravity disappears, but because the word strong no longer captures what is happening. Earlier, you could still compare it to familiar experiences, even if only loosely. You could think of it as an intensified version of what you feel on Earth, scaled up, stretched out, made more extreme. Here, that comparison fades. What you're moving through now is not just a stronger version of ordinary gravity, but a region where the curvature of space-time itself is approaching its limits. The structure that has been guiding your motion, bending light, stretching time, and shaping every path you follow is becoming so tightly curved that the distinctions you once relied on begin to lose their meaning. And yet even now there is no sudden break, no abrupt wall, no sharp boundary that announces, this is the edge. The phrase, edge of nothingness, can be misleading if taken too literally. There is no surface marking a final frontier, no visible line separating one kind of reality from another. Instead, what changes is how the concepts of space, time, and distance behave. You are still moving, you are still experiencing. But the framework that makes those experiences understandable is becoming increasingly strained. The pull you have been feeling, the gradient that stretches and compresses, continues to intensify. Tidal forces, which were once gentle and then noticeable, now dominate the behavior of matter. The difference in gravitational influence across even the smallest distances becomes enormous. It is no longer just your overall structure that is affected. The forces acting on smaller and smaller scales grow significant, reaching into the internal makeup of matter itself. The idea that an object can maintain a coherent shape becomes harder to sustain, not because of a sudden disruption, but because the differences in how each part of that object is pulled become too large to reconcile. Still, this is not chaos. It is structured, precise, governed by the same relationships we have followed all along. Gravity is not acting randomly. It is acting differently across space, and that difference is what creates the effects you're now experiencing. At the same time, something else is happening, something less visible, but equally important. The distinction between space and time continues to blur. Earlier we described how the inward direction becomes unavoidable, much like the flow of time. Now, that idea deepens. The closer you move toward what we call the center, the more this direction dominates every possible path. There is no sideways escape, no alternative route. Every trajectory, every possible motion leads inward. In a sense, you're no longer navigating space in the way you once did. You are progressing along a path that is as fixed as the passage of time itself. And this brings us back to the idea of nothingness. It's not that you're approaching an empty void. It is that the usual structures we use to define something, location, distance, direction, are becoming less meaningful. The singularity, as predicted by general relativity, is often described as a point of infinite density. But from your perspective, it is not something you see ahead like a destination on a map. It is something that defines the structure of the region you're in, shaping every path, every motion, without presenting itself as a visible object. You do not observe nothing. You observe a limit to how far the current description of physics can take you. The environment around you does not become featureless in a simple way. Instead, it becomes increasingly constrained. The variety of possible observations, the richness of available information, all of it narrows. Light, which once carried detailed images of the universe, has already faded to the point where it plays a minimal role. The external universe is no longer a reference. What remains is the local structure, the immediate conditions shaped by the extreme curvature of space-time, and even those conditions are becoming harder to describe in familiar terms. Distances shrink, but not in a straightforward way. Time continues, but not in a way that can be easily compared to anything outside. The closer you move toward the center, the less meaningful those comparisons become. There is also a sense in which the idea of before and after begins to shift. Not because time stops, but because the framework that allows you to relate different moments to each other becomes less intuitive. The path forward is still there, still defined, but the concepts you would use to describe it in everyday language begin to lose their clarity. This is what makes the phrase edge of nothingness feel appropriate, even if it is not literally accurate. You're not approaching a place where something is absent. You are approaching a region where the tools we use to describe something are reaching their limits. The equations of general relativity predict that curvature becomes infinite at the singularity. But as we discussed earlier, infinities in physics often signal that a theory is incomplete, not that reality itself behaves in an unbounded way. So what you are approaching may not be a true point of infinite density. It may be something else, something that requires a deeper understanding, one that combines relativity with quantum mechanics in a way we have not yet fully achieved. From your perspective, however, there is no opportunity to step back and analyze this. The journey continues along its path. The conditions continue to intensify. the structure of space-time continues to guide everything inward. There is a quiet inevitability to this stage. Not dramatic, not chaotic, but absolute. You're moving through a region where the curvature of space-time is so extreme that it defines every aspect of what can happen. The idea of resisting it does not apply. The idea of escaping it is no longer meaningful. And yet, there is still continuity. You are still experiencing one moment after another. There is no break in awareness, no sudden discontinuity in the flow of experience. Even as the underlying physics approaches its limits, the progression remains smooth. This is perhaps the most striking aspect of all. The most extreme environment we can imagine does not present itself as a sudden collapse into chaos, but as a continuation, a steady movement into conditions that become more difficult to describe but not more erratic in how they unfold. Somewhere along the way, as people began to understand just how strange black holes are, a different kind of question naturally followed. If space-time can bend this much, could it also connect? Not just curve inward, not just pull everything toward a centre, but actually link distant regions together in a way that bypasses the usual paths through space. The idea does not come from imagination alone. It comes from taking the equations of general relativity seriously and asking what else they might allow. Among the many solutions those equations admit, there is one particularly intriguing possibility, a structure sometimes referred to as a wormhole. At first, the concept sounds simple enough. Instead of space being a continuous expanse where the only way to travel between 2 points is to move through the distance between them, a wormhole would act like a shortcut, a tunnel connecting 2 separate regions of space-time directly. If such a structure existed, entering one end could in principle allow you to emerge somewhere else entirely, perhaps very far away, perhaps even in a different time. It is a compelling idea, and black holes, with their extreme curvature, seem like natural candidates for something like this. After all, if space-time is being bent so dramatically, could it fold in on itself? Could the inward path you are following lead not just to a central region, but to another location entirely? The mathematics offers hints. Certain solutions to the equations describe what are called Einstein-Rosen bridges, theoretical connections between 2 separate regions of space-time. These bridges resemble wormholes in a basic sense, linking one side to another through a kind of tunnel. But there is an important detail. These structures, as described in their simplest form, are not stable. They pinch off too quickly. If you were to try to pass through such a bridge, it would collapse before you could make it to the other side. The connection exists mathematically, but not in a way that allows for traversal. To keep a wormhole open, something unusual would be required. A form of matter with properties that do not behave like anything we normally encounter, often referred to as exotic matter. This matter would need to have negative energy density, effectively pushing space-time outward, rather than allowing it to collapse inward. As of now, we have no confirmed evidence that such matter exists in the quantities needed to sustain a wormhole. So while the equations do not forbid the idea entirely, they do not make it easy either. From your perspective, continuing inward, nothing about the experience suggests that you are approaching a doorway. There is no branching path, no indication that space-time is opening into another region. The inward direction remains singular and unavoidable. Every trajectory still leads deeper toward the center, not sideways into an alternate route. The structure you are moving through is consistent with a black hole, not a passage. And yet the idea persists, not because it is confirmed, but because it sits at the edge of what might be possible. There are variations on this concept. Some speculative models suggest that what we call a black hole could be connected to something like a white hole, a theoretical object that is the reverse of a black hole, expelling matter and energy instead of absorbing it. In such a scenario, the two could be linked, forming a kind of bridge between different regions. But white holes themselves remain hypothetical. We have not observed them, and their existence raises additional questions about stability and consistency with known physics. There are also ideas that connect wormholes to quantum phenomena. Some physicists have explored the possibility that entangled particles, those linked in such a way that their states are correlated across distance, might be connected by tiny, non-traversable wormholes at a fundamental level. This idea, sometimes summarized as ER equals EPR, suggests a deep relationship between geometry and quantum entanglement. Even in that case, however, these connections do not function as usable tunnels. They are not pathways you could travel through. They are more like underlying structures that relate different parts of space-time in ways that are not directly accessible. So where does that leave the idea of black holes as doors? From a scientific standpoint, the answer is cautious. There is no evidence that falling into a black hole leads to another universe or another distant location. The models we have, based on current understanding, describe a one-way journey inward, not a transition to somewhere else. The geometry you are moving through does not branch. It converges. And yet, the reason this idea remains compelling is not just because of what we know, but because of what we do not yet fully understand. The singularity itself, as we have discussed, represents a limit in our current theories. If that limit is resolved by a deeper framework, one that combines relativity and quantum mechanics, it is possible that new structures could emerge, structures that are not captured by our present models. But that is still speculation. From your current position, there is no indication of such a transition. The experience remains consistent with everything we have described so far. The inward path continues. The curvature of space-time becomes more extreme. The available directions narrow further, not expand. There is also an important distinction to make. Even if wormholes or similar structures exist somewhere in the universe, they would not necessarily be associated with the black hole you are in. The existence of one does not imply the presence of the other in every case. Black holes, as we understand them, are defined by their event horizons and their inward curvature. Wormholes, if they exist, would be separate configurations of space-time, requiring specific conditions to form and remain open. So while the idea of a hidden doorway is intriguing, it does not match the behavior of the system you're currently imagining. The journey remains inward. The structure remains continuous. There is no sudden opening, no branching path, no alternate destination revealed along the way. And yet, the question itself is valuable. It reflects a deeper curiosity about the nature of space-time, about whether the universe allows for connections beyond the obvious, whether the paths we see are the only ones that exist. Even if the answer, for now, appears to be no, the exploration of that question has led to new insights, new theories, and a deeper understanding of how gravity and geometry interact. Far from where you are now, beyond the reach of this inward pull, something remarkable can still be felt. Not seen in the usual way, not heard as sound, but measured as a subtle shifting of distance itself, a stretching and compressing of space that passes through everything without resistance. Even events as hidden and unreachable as what happens around black holes can leave traces, and those traces travel outward as ripples in space-time. These are known as gravitational waves. They were predicted long ago by Albert Einstein as a consequence of general relativity. If mass curves space-time, then accelerating mass should create disturbances in that curvature, waves that propagate outward at the speed of light, carrying energy and information about the motion that produced them. For a long time, this idea remained theoretical. The effects are incredibly small. Even powerful cosmic events produce ripples that, by the time they reach Earth, change distances by less than the width of a proton. Detecting them requires instruments of extraordinary precision, capable of measuring changes in length that are almost unimaginably tiny. But they are real, and black holes are among the most powerful sources of these waves. When two black holes orbit each other, drawing closer over time, they create a pattern of gravitational waves that grows stronger and faster as they spiral inward. The final moments, when they merge into a single larger black hole, produce a burst of energy that travels across the universe, carrying with it a signature of the masses and spins involved. From your perspective, Inside a black hole, you would not perceive these waves in any direct way. There is no sensation of space stretching and compressing around you as a wave passes. The scale of the effect, even near its source, is subtle compared to the overwhelming curvature already present. The dominant experience remains the inward progression, the steady shaping of space-time that defines every path. But from the outside, these waves are a form of communication. They allow distant observers to detect events that would otherwise be invisible. A black hole merger does not emit light in the way stars do. There may be no bright explosion, no visible signal across the electromagnetic spectrum, and yet, through gravitational waves, the event becomes detectable, measurable, and even interpretable. It is as though the universe has found a way to speak, even in situations where light cannot escape. Each wave carries a story, not in words, but in patterns. The frequency of the wave, how quickly it oscillates, tells us about the motion of the objects involved. The amplitude, how strong the stretching and compressing is, reveals how much energy is being released. The way the signal changes over time encodes the dynamics of the system, the gradual in-spiral, the final merger, and the settling of the newly formed black hole. This settling phase is sometimes called the ring down, where the black hole adjusts to its final state, emitting gravitational waves as it stabilizes. Even though you're now inside a black hole, part of a process that cannot be observed directly from the outside, the broader class of events like this remains visible through these ripples. They are echoes of motion, traces of interactions that cannot be hidden completely. There is something quietly profound about that. Black holes, which define regions of no return, still participate in a larger network of cause and effect. Their mergers, their motions, their changes in structure, all of it can influence the universe far beyond their immediate surroundings. Gravitational waves do not get trapped in the same way light does. They are distortions of space-time itself, and they propagate outward regardless of the presence of an event horizon around the objects that created them. The waves are generated outside the horizon, in the motion of the masses as they orbit and merge. This is why they can escape, and this is why we can detect them. When instruments on Earth measure these waves, they are effectively sensing the passage of a distant event, one that may have occurred millions or even billions of years ago. The signal arrives as a tiny oscillation, a rhythmic stretching and compressing of space, but within that signal is a wealth of information. Masses, distances, speeds, the nature of the objects involved. It is a different way of observing the universe, not through light, but through the geometry of space itself. From your current position, this may feel distant, abstract. You're no longer in a place where signals can travel outward to distant observers. The region you occupy is causally disconnected from them. What happens here does not send ripples they can detect, and yet the black hole you are inside has a history. It may have formed through processes that generated gravitational waves. It may have merged with other black holes in the past, sending out signals that are still travelling through the universe even now. Those waves carry part of its story. They are, in a sense, echoes of events that have shaped the object you're now inside. There is also a broader implication. Gravitational waves demonstrate that space-time is not static. It is dynamic, responsive, capable of carrying energy and information across vast distances. The same fabric that is now curved so intensely around you is, elsewhere, capable of vibrating, oscillating, and transmitting signals. This reinforces the idea that the universe is not a collection of separate pieces, but a connected whole. Even the most extreme regions are part of that connection. They may hide certain information, block certain signals, and create boundaries that cannot be crossed. But they do not exist in isolation from the larger structure. They influence it. They leave traces. They contribute to the ongoing evolution of the cosmos. Two stories are unfolding at the same time, and they never quite meet. From where you are, everything has been continuous. You have moved inward, crossed the event horizon without noticing a boundary, watched light distort and fade, felt the gradual strengthening of tidal forces, and followed a path that leads inevitably deeper. There has been no interruption, no freezing, no sense that anything fundamental has stopped working. One moment leads to the next, just as it always has. But far away, someone watching tells a completely different story. They see you approach the black hole, slow down, dim, and linger at the edge. Your movements stretch out. Your signals arrive less frequently. Eventually you fade from view, not because you have vanished suddenly, but because the information reaching them becomes too weak, too delayed, too red-shifted to detect. From their perspective, you never quite crossed the event horizon. From yours, that crossing happened long ago. Both descriptions are correct. This is what makes the observer's paradox so fascinating. It is not a contradiction in the sense of one being right and the other being wrong. It is a reflection of how space-time behaves, how different observers can experience and measure the same sequence of events in fundamentally different ways. The key lies in how time is defined. In everyday life, we assume that time is shared, that there is a single now that everyone agrees on. If two people watch the same event, they may see it from different angles, but they agree on when it happens. Near a black hole, that agreement breaks down. Time is no longer a universal background. It becomes local, tied to the observer's position and motion. What you consider to be happening now is not the same as what a distant observer considers to be happening now. This difference grows as the gravitational field becomes stronger. As you approach the event horizon, your time slows relative to theirs. Signals you send take longer to reach them. The intervals between those signals stretch out. From their point of view, your entire timeline near the horizon becomes extended. But from your point of view, nothing about your own time has changed. This creates two equally valid timelines, one in which you cross the event horizon and continue inward, another in which you approach the horizon forever, never quite completing the crossing. The reason both can exist is because there is no single, absolute way to slice space-time into moments. Each observer has their own way of defining what happens when. The event horizon plays a special role in this. It is not just a boundary in space. It is a boundary in what can be communicated. Once you cross it, no signal you send can reach the outside observer. This means that your timeline and theirs become permanently disconnected in terms of information exchange. They cannot see what happens next. You cannot send them updates. Your story continues, but only from your own perspective. This leads to an interesting realization. The paradox is not about what physically happens to you. It is about what can be observed and described from different locations. From your perspective, there is no paradox. The journey is smooth, continuous, and consistent. You cross the horizon, you move inward, and the effects we have described unfold in sequence. From theirs, the lack of information beyond the horizon creates a different narrative. They see a limit, a boundary where events appear to slow and fade. They do not have access to what lies beyond, so their description ends at the edge. Both are complete within their own frames. Neither requires the other to be wrong. This challenges a deeply held intuition. We're used to thinking that there is a single, objective account of events, one timeline that everyone could agree on if they had enough information. Relativity shows that this is not always the case. There can be multiple valid descriptions, each tied to a specific observer. This does not mean that reality is subjective in the sense of being arbitrary. It means that reality is structured in such a way that different observers, following different paths through space-time, can legitimately disagree about the ordering and timing of events. There is also a deeper layer to this. The paradox highlights the role of information. What you can say about an event depends on the information available to you. The distant observer's description is limited by the signals they receive. Your description is based on your direct experience. The event horizon separates these two domains. It creates a boundary where information flow is one way. Because of this, the outside observer can never update their description to include what happens inside. Their version of your story remains incomplete, not because of a mistake, but because of a fundamental limit. At the same time, your version cannot be shared outward. You cannot confirm your experience to them. This mutual limitation is what gives rise to the paradox. It is not a clash of facts, it is a separation of perspectives, and yet the underlying physics remains consistent. General relativity provides a framework in which both descriptions can exist without contradiction. The equations describe how spacetime is curved, how light travels, how time is measured, and when you apply them carefully, they account for both viewpoints. The paradox dissolves when you accept that there is no single global perspective that everyone must agree on. Instead, there are local perspectives, each valid within its own context. There is something quietly profound in that idea. It suggests that understanding the universe is not just about finding the right answer, but about understanding how different answers can coexist, each tied to a specific way of observing. As you continue inward, your experience remains your own. The outside observer's view remains theirs. The two stories diverge, not because reality splits, but because the structure of space-time allows for multiple consistent descriptions. Eventually, the idea of distance begins to lose its usefulness entirely, not because you have stopped moving, and not because there is nowhere left to go, but because the way you would normally measure how far something is no longer applies in any meaningful way. Earlier, you could still imagine yourself getting closer to something, reducing the space between where you are and where you're going. Now, that sense of approach becomes harder to define. You're still progressing, but it feels less like moving toward a destination, and more like continuing along a path that has no alternative, no branches, no deviation. There is a quiet simplicity to this stage. The outside universe has already faded from view. The light that once carried distant information has diminished to the point where it no longer plays a central role in your experience. The visual field, once filled with distorted rings and shifting brightness, has become minimal, almost still. What remains is not empty in the usual sense. It is structured, but in a way that offers very little variation. The differences that once defined direction, orientation, and reference have been smoothed out by the extreme curvature of space-time. There are fewer cues, fewer changes, fewer markers that allow you to situate yourself in a familiar way, and so the experience becomes more inward. Not inward in a physical sense, but in the sense that your awareness is no longer anchored by an external environment. There are no stars to track, no clear boundaries to observe, no changing scenery to follow. You're still moving, but the movement is no longer framed by anything outside of itself. This is where the idea of falling forever begins to take shape. From your own perspective, the time remaining before reaching the central region is finite. The equations of general relativity suggest that you will not continue indefinitely. There is an endpoint along your path, even if its nature is uncertain. But in the absence of external reference points, that endpoint does not feel like something you are approaching in the usual way. There is no horizon ahead, no object growing larger in your field of view, no clear signal that says you are almost there. Instead, there is continuity. Moment follows moment. The path remains smooth, and without anything to compare against, the passage of time becomes self-contained. This creates a subtle sense of detachment, not emotional in the way we usually describe it, but structural. You're no longer part of the shared timeline of the outside universe. The connection has already been severed. What happens beyond this point is not something that can be communicated or observed from elsewhere. Your experience exists entirely within this region. There is no external observer who can confirm it, no signal that can carry it outward. It is complete in itself, defined only by the local conditions of space-time. There is something quietly isolating about that. not in a dramatic or overwhelming way, but in a simple, undeniable sense. You're following a path that no one else can share, not because others could not imagine it, but because the structure of the universe does not allow that experience to be transmitted back. And yet even here the journey is not chaotic. The same consistency that has guided everything so far remains in place. The curvature of space-time continues to define your motion. The progression of time continues to feel steady. The absence of external reference does not mean the absence of order. It means the absence of comparison. Without comparison, the idea of speed becomes less meaningful. You're moving, but there is nothing to measure that movement against. Without comparison, the idea of change becomes more subtle. Things are still changing, but there are fewer distinct states to contrast. Without comparison, even the idea of before and after becomes more about sequence than about difference. One moment leads to the next, but the distinction between them is less pronounced. This is where the phrase poetic loneliness can feel appropriate, not because the experience is emotional in a human sense, but because it reflects a kind of structural isolation. You're in a region where the usual connections, visual, informational, temporal, have been reduced to their simplest form. There is only the path, there is only the progression, and there is no alternative. At the same time, it is important to remember that this is not an endless process. From your perspective, there is still a finite duration to what remains. The equations do not suggest that you will fall forever in your own time. They suggest that you will reach a point where the current description of physics no longer applies. But because there is no clear marker of that approach, it does not feel like a countdown. It feels like continuation. This is one of the most striking aspects of the experience. The most extreme journey we can describe does not feel like a dramatic rush toward an obvious end. It feels like a steady, uninterrupted flow, one that becomes simpler, more constrained, and more self-contained as it progresses. There is also a sense in which the question of what happens next becomes less about observation and more about theory. You cannot see the singularity. You cannot observe its structure. You can only follow the path that leads toward it, knowing that it represents a limit in our current understanding. And so the experience becomes less about discovering new visual or physical phenomena and more about reaching the boundary of what can be described at all. There is a quiet transition here. Earlier, each stage introduced new effects, new ways of seeing, new changes in how space and time behaved. Now, the emphasis shifts toward the absence of those changes, the reduction of variety, the narrowing of possibilities. The universe, in this region, becomes simpler in what it presents to you, even as the underlying physics becomes more extreme. And in that simplicity there is a kind of clarity. Not clarity in the sense of understanding everything, but clarity in the sense that there is only one direction, one path, one sequence of moments. You are not choosing where to go. You're not deciding what to observe. You are following the only trajectory that exists. As this continues, the idea of falling forever remains as a kind of perception, a way of describing the uninterrupted flow of experience, even though, in a technical sense, the journey has an end point. After everything we have followed, every step inward, every shift in time, every distortion of light, every quiet change in how reality behaves, there is a moment where the focus naturally turns outward again. Not outward in space, because that connection has already faded, but outward in understanding. Because black holes are not just places, they are lessons. Not lessons in the sense of something explained directly, but in the way they force us to reconsider what we thought was certain. Every effect you have imagined, the slowing of time, the bending of light, the separation between observers, all of it comes from the same underlying truth. The universe is not built the way it appears in everyday experience. What feels solid, fixed, and absolute is, in reality, flexible, responsive, and dependent on context. One of the first things black holes teach us is that space and time are not separate. Before the work of Albert Einstein, it was natural to think of space as a stage and time as a clock ticking in the background. But through general relativity, we learned that they are part of a single structure, one that can stretch, curve, and evolve. Inside a black hole, that idea becomes unavoidable. You cannot separate where you are from when you are. The direction inward behaves like time. The flow of time depends on your position. The distinction between space and time, something that feels so clear in everyday life, becomes something fluid. This is not a small adjustment to our understanding. It is a complete shift in how we think about reality. Another lesson comes from the idea of perspective. Throughout this journey, there has never been a single, universal description that everyone agrees on. From your point of view, the fall is continuous. From the outside, it appears to slow and fade. Both descriptions are correct, even though they seem incompatible at first. This tells us something important. Reality does not always present itself as one shared narrative. Instead, it can depend on where you are and how you observe. The universe allows for multiple valid perspectives, each consistent within its own frame, even when those perspectives cannot be easily combined. There is also the lesson of limits. The singularity represents a point where our current theories stop providing clear answers. Not because reality stops, but because our descriptions reach their boundary. This is not a failure in the usual sense. It is a signal that there is more to discover. When equations produce infinities, when concepts lose their clarity, it often means that we are approaching a deeper layer of understanding, one that requires new ideas, new frameworks, and new ways of thinking. Black holes show us exactly where those limits are. They mark the edge of what we can currently describe with confidence, and in doing so, they point toward what remains unknown. There is also a quieter lesson about simplicity. Despite all the complexity we've explored, black holes themselves are described by only a few properties: mass, spin, and charge. Everything that falls in, no matter how detailed or structured, contributes to these simple quantities. This contrast between complexity and simplicity is striking. The universe can take something incredibly detailed and reduce it to a few defining characteristics. And yet, as we've seen through ideas like the information paradox, that simplicity may be hiding a deeper complexity, one that is not immediately visible. It suggests that what we see on the surface is not always the full story. Another lesson comes from connection. Even though black holes create regions where information cannot escape, they are not isolated from the rest of the universe. They influence their surroundings, shape galaxies, emit radiation through quantum effects, and send ripples through spacetime when they interact. They are part of a larger system. This reminds us that even the most extreme objects are connected to the broader structure of the cosmos. Nothing exists entirely on its own. Everything participates in the same underlying framework, the same network of interactions and influences. There is also something to be learned about scale. On human scales, space feels flat, time feels steady, and gravity feels uniform. But as we move to larger scales or more extreme conditions, those assumptions break down. Black holes show us that the universe operates differently depending on the scale at which you observe it. What is true in one context may not be true in another. This does not mean that the laws of physics change. It means that their effects become more or less noticeable depending on the situation. Black holes reveal the full range of those effects. They take principles that are subtle in everyday life and amplify them to the point where they define the entire experience. And perhaps the most important lesson is about curiosity itself. Everything we have discussed, every idea, every theory, every question, comes from the desire to understand something that cannot be directly experienced in a conventional way. Black holes are distant, extreme, and inaccessible, yet we can describe them, predict their behavior, and even observe their effects. This is a testament to the power of reasoning, observation, and imagination. It shows that even when something lies beyond our immediate reach, we can still build an understanding of it, piece by piece, through careful thought and evidence. At the same time, black holes remind us that understanding is always evolving. There are still open questions: the nature of the singularity, the resolution of the information paradox, the relationship between gravity and quantum mechanics. These are not small gaps. They are some of the deepest questions in physics, and black holes sit at the center of them. From your perspective, deep within this imagined journey, these lessons are not something you observe directly. You are still following the path inward, still experiencing the effects as they unfold. But from a broader point of view, this journey reflects something larger. It shows how the universe behaves under its most extreme conditions, and how those conditions challenge and expand our understanding. It shows that reality is more flexible, more complex, and more interconnected than it first appears. Now, instead of moving further inward, allow the direction of attention to shift, not abruptly, not as a sudden turn, but as a gradual easing, the way your thoughts might drift when you realize there's nothing more you need to follow, nothing more you need to reach. The journey we have been tracing does not reverse in a physical sense. There is no path outward from where you have imagined yourself. And yet, your awareness is not bound in the same way. It can step back, it can widen, it can return. So rather than continuing deeper into the structure of the black hole, let the focus soften, expanding gently outward, away from the extreme curvature, away from the narrowing paths, away from the region where every direction leads inward. Picture, if you like, the distant universe again. Not as it appeared distorted and wrapped into rings, not as it faded at the edges of visibility, but as it normally feels. Wide, open, filled with quiet points of light, each one steady, each one following its own slow and predictable motion. There is no need to rush back. The return is not a movement through space, but a shift in perspective. You're no longer tracing the path of a falling object. You're observing the idea of that path, holding it lightly, allowing it to settle into understanding rather than continuing it as an experience. The black hole remains where it is, a region defined by its curvature, its boundary, its quiet intensity. Nothing about it has changed. It has not softened or weakened. It continues to exist exactly as before, shaping space-time, influencing its surroundings, holding within it the questions we explored. But you are no longer inside that path. You are here, considering it. And that difference matters. Because what we have been doing is not falling, but understanding what falling would mean. We have followed the logic of physics step by step, allowing each effect to unfold naturally, without forcing it, without rushing it. We have seen how gravity bends space, how time separates between observers, how light curves, fades, and eventually disappears from view, how matter stretches under tidal forces, how information becomes a question rather than a certainty, how even something that seems completely dark can still emit the faintest trace of energy. And through all of it, there has been a consistent pattern. No sudden breaks, no chaotic jumps, just a steady progression, guided by the same underlying principles. That is one of the most important things to carry with you. Even in the most extreme environment we can describe, the universe behaves in a way that is continuous, structured, and consistent. There is a kind of calm in that. Not because the situation itself is gentle, but because it is understandable, at least in part. The same laws that apply to the smallest and most familiar situations extend all the way to the largest and most extreme. There is no separate set of rules waiting in the dark, only the same rules expressed more fully. And as you let that settle, you might notice how the question we began with has shifted. At the beginning, it was simple. What really happens when you fall into a black hole? Now, the answer feels less like a single statement and more like a journey. It is not one event, but a sequence. Not one perspective, but many. Not one clear image, but a set of ideas that fit together to describe something that cannot be directly seen. and that is enough. There is no need to resolve every uncertainty, no need to answer every open question. Some of the most interesting parts of this topic are still being explored, still being debated, still waiting for deeper understanding. The singularity remains uncertain. The information paradox remains unresolved. The connection between gravity and quantum mechanics remains incomplete. But none of that takes away from what we do understand. It adds to it. It keeps the subject open, alive, continuing. And as your attention continues to drift outward, back toward a more familiar sense of space, there is something else to notice. The scale of it all. The black hole we have been imagining is one object among many. There are countless others scattered across the universe, each one formed through its own history, each one shaping its surroundings in its own way. They are not anomalies, they are part of the natural structure of the cosmos, and yet they still feel special, not because they break the rules, but because they reveal them so clearly. They take the hidden aspects of physics, the curvature of space-time, the relativity of time, the limits of information, and bring them into focus in a way that cannot be ignored. They are, in a sense, places where the universe explains itself, slowly, quietly, without urgency. And now, as the journey comes to rest, there is no sharp ending, no final moment where everything stops, just a gradual settling, a return to stillness where the ideas remain, but the movement through them slows. You can imagine yourself once again far from the black hole, looking out into a calm, open expanse of space. The stars are steady. The patterns are familiar. Time feels uniform again, not because it has changed, but because you are no longer in a region where its differences are so pronounced. Everything feels aligned, simple, quiet. And if you think back to the beginning, to that first question, there is a different kind of answer now. Not a single explanation, but a deeper sense of what it means to ask it. What happens when you fall into a black hole is not just about the fall, it is about how the universe works when pushed to its limits. It is about how perspective changes what we see. It is about how even the most extreme conditions follow patterns that can be understood. And it is about how much there still is to learn. So as you rest with that, there is nothing more you need to follow, no further step to take, just the quiet understanding that the journey has unfolded exactly as it needed to, and that you can return from it not by escaping, but by simply letting your attention settle back into the familiar, carrying with it everything you have seen, everything you have considered, and everything that remains gently open for the next time you choose to explore it again.